Hello, everyone. I'm Zhao from Kidami Institute of Technology, Japan. On behalf of the committee members of the 10th EAI International Conference on Mobile Networks and Management, it's my great pleasure to invite all of the great scientists, academics, young researchers, and students from all over the world to attend MONAMI 2020. Well, it is a big pity that the conference cannot be held in Chiba, Japan. But consider that so many people have suffered from the virus. There is currently no guarantee of a return to the normal. Today, we are finally able to gather for MONAMI 2020. This in itself is a great victory against the disease. In addition, the pandemic has also given us a chance to reconsider how our professionals can overcome unknown future disasters. The success of the conference ultimately depends on all the members who have worked extremely hard. Please let me express my greatest appreciation for Professor Imrich Klemtek, conference manager Angelica and Christina for their wise advice and brilliant suggestions. Many thanks to the co-organizers Prof. Kui Wu, Tan Hui Ping, Seng Lok, Zhi Liu, and Qiang Nguyen, and all the committee members for their timely, hard work. In addition, we are privileged to welcome Professor Jiang Chuan Liu of Simon Fraser University, Canada, Professor Yusheng Ji from National Institute of Informatics, Japan, Professor Mianxiong Dong from Roland Institute of Technology, Japan, and Professor Jianping Wang from City University of Hong Kong as keynote speakers. Thank you very much. This year, the conference will be devoted to the topic of intelligent mobility and edge computing for a smarter world. This conference gets into the heart of all matters relating to mobile computing and communications, and it brings together the best scientists from around the world, allowing you to hear and meet those at the forefront of our practice. I'm sure that each one of you will identify subjects of interest and will benefit from many fruitful and enriching discussions. Let's enjoy the conference. Thank you very much.
Dear ladies and gentlemen, let me welcome you to the EAI MONAMI 2020, the 10th EAI International Conference on Mobile Networks and Management. My name is Kristina Petrovichova and I am the Conference Manager of MONAMI 2020. Unfortunately, due to the COVID-19 emergency, I'm not able to meet you all in person. Therefore, I'm using this opportunity to address the organizing committee, the keynote speakers, the authors and the participants on behalf of the European Alliance for Innovation. Thank you for being a part of this conference. In particular, I would like to thank the General Chair, Professor Zhao from Kitami Institute of Technology, together with the whole organizing committee, for their hard and excellent work throughout the whole process of conference preparation. During today's event, there are truly many ways how you can actively participate and enjoy the online interaction. During the streaming, there is a Slack platform available for all of the participants where you can discuss the presentations and participate in Q&A sessions. Upon accessing the link below for MONAMI 2020 workspace, you can enter all channels which are divided into sessions. Moreover, you can vote on individual presentations and leave your fellow presenters feedback via EAI Compass. In a moment, we will show you how you can access these platforms and make the most of this unique online experience. I would also like to use this opportunity to invite you to join us for the next edition of MONAMI, which will be held in September 2021 in Chiba, in Japan. We will keep you updated and the news about this event will be available on the conference website. Should you be interested in becoming a part of the next year edition, organizing committee, or the technical program committee, please do not hesitate to contact me at my email address below. In addition, if you are interested in organizing an event with EAI, such as a conference, a workshop, or a seminar, please do not hesitate to contact me at my email address as well. I will be happy to provide you with more information. Now, our community manager Michal will talk more about what EAI does, who we are, and how you can get involved in our various activities. Thank you for your attention. I'm looking forward to meeting you at MONAMI 2020 in Chiba, in Japan. Enjoy this conference.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hi, everybody. It's nice to meet you here. This is Jianping Wang from City University of Hong Kong. Some people think that we are far away from fully automated driving, where some people think that we are very close to autonomous driving. No matter how we think, there's no doubt that autonomous driving is gaining momentum in intelligent mobility, which is one of the main themes of this conference. Today, I would like to share some understandings on different aspects of autonomous driving. In this talk, I will introduce the main software modules in an autonomous driving system, their latest developments, some work from my group, and the future research of autonomous driving. Now, let us take a look at autonomous driving. I will briefly introduce the different levels of autonomy, software components of autonomous driving system, and edge computing assisted autonomous driving. There are 6 levels of vehicle autonomy, from both eyes-on and hands-on to eyes-off and hands-off. The higher the automation level is, the more tasks are taken over from the driver. Among these 6 levels of autonomy, our ultimate goal is to reach level 5, which requires no human interventions under all conditions. There's even no steering wheel or acceleration or braking pedals. In full automated driving, there are mainly 4 software components: environment perception, localization, planning, and controller. The environmental perception is to detect and locate the nearby objects based on image data and point cloud data. Localization is to locate the ego vehicle in space by using like a GPS, high-dimension maps, and IMU. Planning, we have global planning and local planning. Global planning is to decide a route to the final destination. Local planning is also called motion planning, which is to generate a collision-free path from the current position to the immediate goal position. Controller is to output steering, throttle, brake, and gear commands to precisely follow the planned trajectory. The success of autonomous driving heavily relies on the safer operation of vehicles, which demand millisecond scale response time. These challenges poses incredible demands to computing resource, thus fosters the marriage between edge computing and autonomous driving. Edge computing enables computing tasks to be offloaded from onboard computing units to edge servers. Moreover, under severe weather conditions, sensors may not work well to detect the surrounding environment. Under such circumstances, edge computing can provide perception information to vehicles. So now, based on the overview, I will talk about the latest development of those key software components and edge computing for autonomous driving. Environment perception includes object detection and object tracking. There are many 3D object detection methods. We can divide them into 3 categories: monocular image-based methods, point cloud-based methods, and fusion-based methods. Many models have been developed in recent years in each category for more accurate and faster object detection. However, there are space for improving. For example, light and weather conditions can affect the performance of cameras and how we can design more robust algorithms and models so that the weather will not affect the performance of cameras. Also, the LiDAR's price is quite expensive, and also humidity affects the performance of LiDAR. For the fusion-based method, it requires on-site collaboration among sensors, which makes this type of models time-consuming and laborious. For object tracking, commonly used object trackers rely on some data association techniques and also traditional filtering methods. In recent years, deep learning has also been applied to the problem of tracking, particularly for images. For example, tracking in monocular images can be achieved in real time through a CNN-based method. For localization, there are 3 types of approaches for localization. GPS IMU fusion-based localization is mainly used for global routing, since the accuracy is quite low. Simultaneous localization and mapping does not need any prior map information. It builds up map while conducting localization. It is more accurate, however, it requires more computational power. Prior map-based localization needs a pre-built map. It matches the position by comparing the online readings with the information in the pre-built map. So most of the time, this matching is quite time and resource consuming. For the planning module, as we mentioned, it including global planning and the local planning. The global planning is to find a route on the road network from the origin to the final destination. So this one is usually formulated as found an end-to-end shortest path in a directed graph. There are several algorithms can do global planning. For local planning, the goal is to generate collision-free trajectories to complete the global plan. There are several types of algorithms for motion planning, and in recent years, deep learning and reinforcement learning based local planners started to emerge as an alternative. The work in this area includes imitation learning and end-to-end learning, for example, to derive trajectory directly from perception. For the controller, it depends on the reference trajectory provided by the motion planner. The controller's goal is to optimize that trajectory. So the optimized trajectory can be approximated to the reference trajectory as much as possible and executed by the vehicle through a sequence of control commands, including the commands for steering, brake, and throttle. For the edge computing assisted autonomous driving, for the vehicle networking, it has been studied for a long time. A lot of research has been done on cooperative sensing and cooperative driving, such as platoon-based driving. In recent years, people started to study how edge computing can assist the autonomous driving. For example, which tasks should be offloaded to the edge and which tasks should be executed on board, and how we can handle the changing network situations, and how we can co-schedule between onboard systems and edge systems. Now, I would like to present a few studies that we have done in autonomous driving, also from those 4 software components perspective. So perception systems of autonomous driving counts on camera and LiDAR as we just introduced. These devices are vulnerable to optical signal attacks. For example, camera can be blinded by strong light. LiDAR can be interfered by receiving counterfeit optical signals. Such physical attacks could compromise the accuracy of object detection, thus cause some driving safety issue. To address this critical issue, we proposed a framework to detect and identify sensors that are under attack. The work has been recently accepted by IEEE Internet of Things journal. We developed a framework where any sensor attack can be detected, and if there are n sensors in the system, as long as no more than n-3 sensors are attacked simultaneously, we can identify the attacked sensors. This slide shows a simple system with 3 sensors, either all camera or 2 cameras and one LiDAR. We build up the depth information of each sensor data and generate the disparity map between sensor with the reference sensor. Then we compare the disparity map and calculate the disparity error. If the disparity error is higher than a threshold, then we detect the attack. Otherwise, we say that the system is normal. This is the experiment result with 4 sensors in KT dataset. We can see that if one sensor is under attack, it will affect all the disparity errors involving that sensor. Thus, we can identify the attacked sensors. If we take a look at this example, say if there's no attack, in this example, we take sensor 3 as a reference sensor. So if there's no attack, then this blue bars shows the disparity error distribution. However, if S0 is attacked, then it will affect all the disparity error involved S0, like E013 and E023. And then, for this disparity map of E123 will not be affected. So according to this, we can identify that S0 is attacked. And if the reference sensor S3 is attacked, then it will affect all the disparity errors. So we can identify which sensor is attacked. In recent years, many adversarial attacks have been studied. The main idea of adversarial attack is to leverage small changes in the input to trigger significant errors in the output of deep learning models. In the literature, the effect of adversarial attacks is measured by the change of average precision. Some models' average precision may change a lot under attack, which however may not cause a serious driving safety issue. This motivates us to study how much these attacks can impact driving safety of vision-based autonomous driving systems. We mainly examine perturbation attack, patch attack, and blind attack. We conduct different types of attacks on the image and feed them to the object detection module and the motion planning module. Similarly, the original images are also input to the same object detection module and the motion planning module. Specifically, we choose stereo RCNN and DSGN as the object detection module and A* as the motion planning algorithm. To further investigate the impact of attack, we adjust the attack intensity, ego vehicle intention, and initial speed during the experiments. The trajectory generated on the attacked images and the ones generated without attack are compared in terms of collision rate and trajectory shape. Furthermore, we also compare the success rate of motion planner generating feasible trajectories in the attacked scenarios and the non-attacked scenarios. This is one ongoing work. Still, for motion planning, besides the traffic environment and road condition, different driving styles of the ego vehicle and the surrounding vehicle can also affect the driving decision. For example, as you can see in this figure, under the same surrounding environment, the aggressive driver makes a lane change decision at the moment when the preceding vehicle is taking lane changing actions, where the conservative driver maintains a safe distance and keeps driving in the current lane until the preceding vehicle has completed the lane change. We can also see that the driving style's impact on lane changes can be reflected by different trajectories and speed distributions. This motivates us to integrate driving styles to design a new lane-changing decision-making models. We use different CANs to extract the driving style of the ego vehicle and the surrounding vehicles from their historical trajectories. The extracted driving styles, together with the 10 traffic factors, are input to the fully connected layers to output the lane change decisions. Our model can be not only used as a decision-making layer in an autonomous driving system, but also applied in the traffic simulators to simulate the human-like traffic flow. From this experiment result, we can see that with the driving style of both the ego vehicle and the surrounding vehicles, our accuracy can reach 98%. Without any driving style incorporated, the overall accuracy is only 83%. And if we only have the surrounding vehicle's driving style without the driving style of the ego vehicle, the accuracy rate is 87%. Without the surrounding vehicle's driving style, if we only have the ego vehicle's driving style, then the overall accuracy is 95%. Now let's take a look at our motion planning work. The work we have done on motion planning is to see how we can quickly find a collision-free human driver-like trajectory. We take the sampling-based motion planning family as the motion planning algorithm. As we can see from this slide, if the sample points are uniformly generated, we need to generate more points, including the red points and the green points. If we can predict the intentions of the surrounding vehicles, we know the future positions of the surrounding vehicles. So the points, some red points should not be sampled. If we can learn from the human driver's trajectory, we know some red points can be further eliminated. So overall, only essential sample points, as we dotted those green points, should be supplied as an input for the motion planning algorithm. This will speed up motion planning process and generate more human driver-like trajectory. This motivates us to design a new motion planning framework by predicting the intentions of the surrounding vehicle and imitation learning. Our proposed framework consists of 3 modules, namely prediction module, sampling module, and planning module, respectively. In the prediction module, we predict the surrounding vehicle's intention based on their historical trajectories. And for the sampling module, we generate sample points near the human driving trajectory, giving the current and the predicted environment information, the initial state and the goal state. For the planning module, we take the set of sampling points generated from the sampling module and the initial state and the goal state and supply it to the sampling-based motion planning algorithm to generate a collision-free and smooth trajectory. With the prediction of surrounding vehicles' intention, our solution can find a feasible trajectory even when the replanning time interval is long. If you look at this table, for this bias uniform sampling and the bias Gaussian sampling, when the replanning time interval is 200 milliseconds, they cannot always find a feasible solution. And our solution can find a feasible solution even when the replanning time interval is 600 milliseconds. Secondly, if we compare our solution with BIOS Gaussian solution based on motion planning, we can see the acceleration change in our solution is not as sharp as those in BIOS Gaussian. That means we can generate a smoother trajectory. If we look at this table, we can see because we supply less number of sampling points, but those are essential sampling points. So our motion planning algorithm can find the feasible trajectory in a shorter time duration. We have another work is to model the interaction among autonomous vehicles. Modeling the interactions among vehicles have been considered essential in improving efficiency and safety in the autonomous driving, since the real traffic scenarios such as merging lanes, intersection, and lane changes are full of complex interactions. Given a traffic scenario, some surrounding vehicles have higher influence on the ego vehicle, while some have less influence. Moreover, such influence changes dynamically. For example, in this example, vehicle 3 is more influential than other vehicles to the yellow ego vehicle. If we can predict whether vehicle 3 is accelerating or decelerating based on the change of its influence on the ego vehicle over a shorter time period, the ego vehicle can make a better decision on whether to act aggressively or yield. So this motivated us to quantify the interaction among vehicles. In the literature, interaction is considered implicitly in individual tasks, which makes it hard to extract interactions for other related downstream tasks. We designed a new model, graph self-attention network, to extract the interaction embedding from the historical trajectories. The trained interaction information by the proposed module can be simultaneously fed into different downstream models. For example, for trajectory prediction, for merging, and for lane changing models. So with the help of our proposed module, the downstream task model can clearly know which surrounding vehicle it should pay more attention to. We use trajectory prediction task as an example to validate that integrating our proposed model into trajectory prediction task can improve the performance of trajectory prediction. We evaluate our model on two well-known trajectory prediction datasets, NGSIM I-80 and US-101. We use the same experimental settings and evaluation metrics as those baseline models. And so we can report the result in terms of root mean squared error. As we can see, the root mean square error in our solution is less than other state-of-art baselines. Now, I would like to briefly talk about the future work of autonomous driving. Considering the impact of weather conditions on the performance of sensors and various physical attacks and adversarial attacks, perception in autonomous driving calls for faster, more reliable, and robust models and algorithms. For localization and planning, it calls for higher accuracy, less time consuming and resource consuming solutions so that a more comfortable and safe trajectory can be generated. From the localization perspective, it calls for high-dimension maps covering more traffic scenarios and more optimized SLAM solutions. From the motion planning perspective, we need to find the right integration between traditional motion planning algorithm and deep learning-based motion planning so that fast trajectory with a safety guarantee can be found. In edge computing assisted autonomous driving, high mobility causes a few new issues, such as dynamic resource allocation, task scheduling, task migration. Security and privacy also need to be addressed, since vehicles do not trust each other. We know drivers with different driving styles may make different driving decisions. Even if they make the same decision, drivers with different driving styles may generate different trajectories. So those human factors highly affect the current and also future transportation systems. The question is how we extract and represent driving styles more accurately and properly, and how we can integrate such information to improve autonomous driving. Autonomous driving will make a lot of changes to mobility. It will stimulate research other than the autonomous driving itself. For example, from policymaking perspective, we need to design appropriate standards for liability, for security and data privacy. And for the infrastructure, we may need more specialized roadside sensing equipment and edge servers to help autonomous driving. And one day, autonomous driving will will be used for taxing services. How we can schedule those robot taxi to maximize the utilization and reduce traffic congestion, and how autonomous vehicles can be shared among passengers, and whether we can design new schemes so that a limited number of autonomous vehicles can help improve the traffic condition and solve the traffic congestion problem. All these are the opportunities. This is an area full of research opportunities. Thank you.
Hello everyone, this is Yusheng. I'm from the National Institute of Informatics, Japan. Today, my talk is about learning to gain better experience for adaptive video streaming. I'd like to acknowledge that a large part of the work introduced here are joint works with my former student, Jiang, and many other colleagues. This is the outline of my talk. First, I will give an introduction on adaptive video streaming, on its background and challenges. Then I will focus on the first topic, which is live video streaming. After that, I will focus on VR streaming or 360-degree video streaming. Also introduce our work on viewport prediction for VR video streaming. Finally, I will conclude my talk and give some future perspectives. According to Cisco's global IP traffic forecast, during 2017 to 2022, the percentage of Internet video traffic among total IP traffic will increase from 75% to 82%. Among Internet video, two new types of video are becoming popular. One is live video. It was 5% of Internet video traffic, but will be 15 times more and reach 17% of the total Internet video traffic. Also, VR traffic will increase more than 10 times, reach about 4 exabytes per month by 2022. All this show that more people are watching video in the Internet, and live video streaming and VR video streaming are becoming more and more popular. And with the COVID-19 pandemic, there will be even more video traffic than the prediction. While watching videos, viewers may often face some annoying scenes. For example, due to the low bandwidth, one may watch very low quality videos without even knowing what is inside the scenes. In the other case, at the beginning, the bandwidth was enough and the users can watch high quality video, but after a little while, the bandwidth may decrease significantly and the video stops playing. The low quality video and frequent rebuffering events, as well as many other factors, may hurt users' experience while watching videos. What are the challenges for video streaming? First, the network bandwidth is limited and usually unstable. On the other hand, in order to gain better experience for viewers, there are conflicting quality metrics. These are two universal challenges which are faced by all kinds of video streaming scenarios, like VOD, live video, or VR videos. That's why we need to stream video to adapt to the network conditions to gain better quality of the experience. For live video streaming, besides of these two challenges, since we need to deliver unknown video information to users in real time, latency becomes a more critical issue. And for VR video streaming, due to the huge amount of video data, like a 360-degree video, for example, or even up to 6 degrees of freedom video, like hologram video, which requires a very large bandwidth. A commonly used way is to divide the whole video frame into tiles and adapt the stream strategy with users' viewing area. As we know, dynamic streaming over HTTP is a standard framework for adaptive video streaming. In a Dash system, when a video is recorded, the whole video will be divided into multiple segments. Each segment has several seconds of duration. Then each segment is encoded into different quality levels. These video segments will be stored in the HTTP server, as in the right-hand side of the figure. along with the media presentation description file to include the media information about the video. At each adaptation step, the ABR adaptive bitrate controller at the video player in the left side will decide which quality level of the next video segment to request to the server, based on the estimated network bandwidth and buffer occupancy level. Then the HTTP server will send the requested video segment to the client. The design of an ABR controller can largely affect the viewer's viewing experiences, and we will face many challenges for designing a good ABR algorithm. Let us consider the factors affecting the quality of experience. How to effectively measure the quality of experience is an important issue which affects the video streaming strategies. For objective quality assessment, picture quality would be a dominant factor of QoE. Usually, it can be measured by resolution, we call bitrate for adaptive video. The higher the better, but more bandwidth is needed for streaming. Picture quality can also be measured by distortion or the structural similarity of received video sequence with the original one. Beside the video quality, the timing smoothness is also important. We don't want stalling or rebuffering for VOD streaming. We also don't want to skip frames due to large latencies in case of live streaming or real-time videos. The quality smoothness can also be an important factor for users' experience. Temporal smoothness concerns the frequency of switching among different picture quality levels, and the spatial smoothness concerns the quality difference within a video frame. There are also subjective QoE assessment. The most direct way to assess QoE during a video streaming session is to ask a limited number of human subjects to watch video in a controlled environment and give opinion scores based on their viewing experience, which is called Mean Opinion Score, MOS. We now look in more details at live video streaming. In live video streaming, we have several control parameters. The first one is the bitrate level. We can choose one of the existing bitrate levels. The higher the better. Since we don't want the video to stall or have long latency for live video, we need to adjust the playback speed accordingly. One way to do that is using the target buffer level, that is, the amount of video stored in the buffer. We can set a threshold for the target buffer level, and if the target buffer level is lower than the threshold, we need to slow down the playback for less stalling. And if the target buffer level is higher than the threshold, we can speed up the playback for less latency. And since we don't want large latency for the live video, we also need a latency limit. If the latency becomes larger than the limit, then we have to skip remaining frames, which will affect the quality of experience. As a result, the QoE function can be defined like this equation, which is from the last year's ACM Multimedia Conference on Live Video Streaming Grand Challenge. Here, QRN is the video quality, TN is the rebuffering time, and LN is the latency. The bitrate level switching is expressed by the difference between two consecutive video segments, QRN plus 1 minus QRN. And SK is the skipping of video frames. For adaptive video streaming, there had been many researches taking different approaches, from heuristics, model predictive control, MPC, optimization-based approaches, to machine learning, especially deep reinforcement learning, with more advanced control methodologies, usually at the expense of more control overhead. We can gain more adaptivity to the dynamics. For example, for live video streaming, heuristic algorithms do latency control by either frame skipping or playback control, but MPC or deep reinforcement learning method can do both frame skipping and the playback control. Given the dynamic network environment, in order to optimize the control parameters for the best QoE, machine learning can be a good approach to find a suitable solution. Specifically, deep reinforcement learning provides a general framework where we can train a neural network agent from the observations instead of designing fixed rules based on heuristics. In a reinforcement learning neural network, the agent can interact with the environment. At each time step, the agent observes from the environment, which is the live video player at the right-hand side of the figure, and get the environment states like the network throughput, buffer level, and the video sizes, and take an action, which can be a combination of video quality level, latency limit, and the target buffer level. As a feedback to the action taken, the environment returns the agent a reward, here defined by the QoE function, indicating how good the action is. The goal of reinforcement learning algorithm is to select the best action sequences, which can maximize the sum of received reward. This is the detailed DRN neural network architecture we have proposed, called HD3, Distributed Dueling DQN with Hybrid Action Space. To be different from the conventional dueling DQN, which can only handle problems with discrete action space, HD3 can take an action with both discrete and continuous values of actions. A DQN utilizes a neural network to construct a discrete action value function dq as a theta to estimate the return or long-term reward the agent can receive under any state action pairs. Then, any state S, the agent will select the action A, which yields the largest value of reward. After downloading live video segment, the agent observes the state ST, which includes the historical information such as throughput, delay, skip time, and the next segment size, which can be observed or estimated, as well as current information of buffer level, bit rate, buffer level on the server, etc., from the environment, and takes it as input to the neural network. In the action task, we need to take hybrid actions, including both discrete and continuous values. More specifically, we need to set a continuous scalar value for the latency limit and make choice from discrete available bitrate levels and the target buffer levels. This figure compares HD3 with several state-of-the-art DRL algorithms in 4 kinds of network conditions with high, medium, low, and changing network bandwidth in live video streaming scenarios. Results are normalized against the performance of HD3. We have trained a single model with each DLL algorithm in a mixed dataset consisting of these four kinds of network traces, and HD3 can achieve the best performance in all four network conditions. HD3 reveals a better performance might because that the dueling DQN-based architecture can properly handle the variance in the mixed training data traces, and the capability for handling hybrid actions makes it less possible to miss the optimal latency limit values. Next, we look at VR video streaming. Virtual reality is a rendered environment providing an immersive experience to users who can interact with it using a head-mount display or an application for the VR. 360-degree video, which involves a 360-degree view of the scene captured from a single point by an omnidirectional camera, can form a main part of VR content to provide an immersive virtual environment. This table from Huawei iLab shows the network bandwidth requirements for different resolution videos. The higher stages of immersion need higher resolution video from 4K to 24K, thus requiring much larger bandwidth up to 5 gigabit per second. In this case, 360-degree video streaming will bring a big challenge for current mobile networks, even in the 5G era. So here comes the challenge for VR video streaming, that is, how to transmit high-resolution videos with limited bandwidth. For 360 videos, the viewer is facing a certain direction at any given time. The viewport can typically cover only 20% of the whole sphere, and it's the only portion needed to be rendered and displayed. So to save the bandwidth, we only need to transmit the viewport part in high quality. Based on this motivation, a tile-based streaming is proposed by the research community. It divides the video of a whole sphere into multiple tiles, for example, 6 by 4 tiles in this figure. Each tile is made available in a set of quality levels. If we know where in the sphere the user is viewing, we can prefetch higher quality tiles for the area covered by the user's viewport, as far as the bandwidth is available. However, to gain better quality of experience for tile-based video streaming, we have two tasks to do. The first one is the viewport prediction, that is, to accurately predict viewers' future viewport for fetching the next video content. The second task is tile bitrate selection, to choose the bitrate for each tile under dynamic and uncertain network conditions. In this selection, a large action space is induced by tiling. That is, for example, for 360 video, we need to select the bitrate for each tile instead of for the whole segment. As for QE metrics, we have video quality, that is bitrate, rebuffering time, spatial variance of content quality, and bitrate fluctuations. There have been researches in tile-based adaptive video streaming since around 2017. The proposed algorithms, including using heuristics, optimization-based method, model predictive control, greedy algorithms like beam search, and deep reinforcement learning, The adaptivity to network dynamics can be increased with more sophisticated algorithms, but the overhead will also be higher. By using machine learning, both spatial and temporal smoothness can be considered. I will briefly introduce our work using reinforcement learning. This figure shows a diagram with modules for the two tasks, viewport prediction (VPP) and tile bitrate selection (TBS) for tile-based adaptive video streaming. The state buffer in upper left collects information from the head-mount displays or 360 video applications and sends the information to the VPP and the TBS agents to make orientation prediction and bitrate decision. The VPP agent predicts future viewport based on the information of historical viewports from the state buffer. To handle potential viewport prediction errors, VPP divides tiles into several areas and sends the tile area map to TBS agent. Finally, the TBS agent selects bitrate for each tile area based on the state buffer information, including historical throughput, historical viewport prediction accuracy, and the size of each tile area, current buffer size. I will go in more details on each part. Here shows an orientation prediction model based on long short-term memory neural network, which is good at time series forecasting. There are mainly two layers in the model, the LSTM layer and the transform layer. LSTM layer takes the orientation of past M video frames as input. Here, the input xt has the value of yaw and pitch, which are the orientations around the areas, axis of y and x. Then the transform layer converts the output y of LSTM layer to the predicted orientation OT. The model can predict future orientation of only one video frame at a time, but we can easily predict the next n orientations by making the last prediction as input repeatedly. Then we can calculate the viewport area according to the collected orientations in one downloaded video chunk. Also, the LSTM-based model can predict at a relatively high accuracy prediction area. Error may also happen, especially when the prediction window is long. So how to handle the potential prediction error can also affect the streaming experience. In the figure, the red square represents the predicted viewport, and the blue square means the actual viewport. As shown in the figure, for both chunk 1 and 2, there are prediction errors of the viewport. To handle the error, we group all the tiles into 3 areas: viewport, adjacent, and out areas. The viewport area has the standard viewport size. Each predicted viewport tile is colored with orange. To handle the potential error for the prediction, we enlarge the viewport area as adjacent area to cover larger angle, such as 90 plus V degrees in vertical and 110 plus H in horizontal, as marked in green color. Then all the remaining tiles will be classified as outside area, as marked with gray color in the figure. Then we can select higher bitrate for not only the viewport tiles, but also the adjacent tiles to cover the actual viewport. The values of H and V should depend on the accuracy of the viewport prediction. For the tile bit rate selection, a deep reinforcement learning network is used. The figure shows the A3C reinforcement learning network used for our proposed algorithm called Plato. First, the state space needs to include all the information that is relevant to make bitrate decisions. Those states include network throughput, chunk download time, size of viewport, adjacent and out areas, current buffer size, last chunk bit rate, and the accuracy of previous prediction, etc. Then the action space. The action to be taken should be the bit rate for each tile area in the next viewport. If the number of tiles is t and the number of bitrate levels is b, the size of action space will be b to the power of t. As the feedback, the reward signal can be derived directly from the QoE metric, which considers the 4 QoE factors: bitrate, rebuffering, variance of the tile quality, smoothness for bitrate changing. In this slide, we show Plato's performance on the individual terms of the QoE function. We use two comparison schemes. Here we call them FDA and MM. Both are published at ACM Multimedia Conference. We compare with each metric independently in terms of the average bit rate in the viewport area and the penalties from rebuffering, spatial variance, which is CV, and the temporal smoothness. From the figure, we can see that Plato can achieve higher average bit rate with a similar rebuffering time penalty. Plato also has better spatial and temporal smoothness than the MM scheme. The reason is that by learning from a trace, the TBS agent can have some foresight to achieve better performance. In terms of CV, the spatial smoothness, only FDA is a little better than Plato. This is because FDA only have 2 kinds of areas, but Plato needs to select bitrate for 3 kinds of areas. This makes Plato a larger quality of difference among the tiles. There are 2 major kinds of approaches for viewport prediction. One is to use the historical trajectory of user head movement to predict future movement. Another is based on video content. These 2 approaches can also be combined. On the other hand, high overhead or cross-user trajectory-based prediction make the models difficult to be deployed in live video streaming or at mobile devices where computational resources are limited. I'm going to introduce a viewport prediction scheme called SVP using linear regression and sinusoidal values of viewing angles, which has low overhead and high prediction accuracy and can be adopted to both 360 VOD and live videos. Let's first examine these 2 figures. The figures show the CDF of prediction error for the yaw and the pitch directions for different time windows. We can observe much larger prediction errors in yaw direction. This is because people's head usually move more in horizontal direction and keeps comparatively stable in vertical direction. Another observation is representing angles with cosine and sine can avoid the periodicity issues. In the left figure, we can observe that while user's head is moving between 180 degree and minus 180 degree, the cosine, that is the red dashed line, and the sine, the blue dotted line, of the angle remain stable. The figure in the right-hand right-hand side shows the predicted values of modules trained with degrees and sinusoidal values. We can find that model trained with sinusoidal values, the red dashed line, can avoid the periodicity issue and get much less error than the model trained with degrees, that is the green dotted line. This figure shows the prediction errors in your direction for 4 prediction schemes, which are linear regression trained by gradient descent method, LSTM neural network, multi-layer perception neural network, and linear regression use least square method. We can see that using sinusoidal value can improve the prediction performance for all schemes and for all prediction windows. Based on the above analysis, we designed a sinusoidal value-based viewport prediction system, which is shown in this figure. The system includes 3 stages. At stage 1, we use sinusoidal value for head orientation prediction to reduce the prediction error. At stage 2, prediction error are handled by dividing the whole area into 3 kinds of tiles: viewport tiles, adjacent tiles, and out of viewport tiles. And at stage 3, we assign all tiles a viewing probability to be sent to the ABR control module. This figure shows the CDF of total bit rate in viewport area during streaming sessions of 3 viewport motion trace datasets. There are 4 comparison schemes. ERP is a naive scheme with no viewport prediction. LR uses single user trajectory. CLS utilizes cross-user trajectories, and OPT, the optimal scheme, assumes that the user trajectory is known. SVP yields higher bitrate than the comparison schemes, except the optimal. We have looked at adaptive video streaming with examples of live video streaming and 360-degree video streaming. By defining the quality of experience for different kinds of video streaming, we can design an ABR algorithm to utilize the limited network resource and gain better user perceived quality. As the content delivery scenario becomes more and more favorable and attractive to users, it induces more control complexities. Thanks to the advancement of machine learning techniques, which can be applied for accurate predictions and making decisions for a huge amount of choices. As learning-based adaptive video streaming algorithms, the deep reinforcement learning is very promising for adaptive control problems. The reward function can be defined according to the quality of experience metrics. By training the neural network in a direction that can increase the gain of QoE, we can deal with a large action space as well as action with continuous and discrete values. Besides, distributed version of DRL can save time on testing hyperparameters or reward function designs. By predicting users' viewing angle in 360-degree video, we can utilize the limited network resource to deliver video content more efficiently. By knowing the features in user behaviors and present them properly, such as head moving velocity and periodicity avoidance, we can gain more accuracy for viewport prediction. It is said that holographic communication will be the next frontier for 6G mobile systems. Similarly, hologram video or volumetric media is being focused by research communities, since it can provide users with more immersive viewing experience by up to 6 degrees of freedom. The most popular way for presenting hologram video is using point clouds, which are composed of points represented in 3D space, and each point is associated with multiple attributes such as coordinate and color. As point cloud video has abundant presentation capability, it has a huge amount of data. In addition to the volume of data, the large computation complexity for decoding makes the point cloud video streaming big challenges in both communication and computation demand. Here again, tiling and viewing angle prediction are seen as effective approaches for reducing the amount of data to be transmitted through the network, and also motivates us to explore the computation capability at the edge, as shown at the end of this table. This concludes my talk. Thank you.
Hello everyone, my name is Xianfu, and I am now working as a senior scientist at VTT based in Oulu. I really appreciate this opportunity for sharing my research. The topic of my presentation is Machine Learning Empowered Multi-Access Edge Computing in Beyond 5G Networks. This is the outline of this presentation. First, I will quickly introduce the background of the talk. Then we will see how we adopt machine learning to solve the problem of multi-access edge computing. After that, I will show some preliminary results from our recent publications. In the end, I will make some conclusions. 5G is now in commercial development phase, which provides the diverse services including enhanced massive broadband, ultra-reliable and low-latency communications, and massive motion type communications. Unfortunately, not all of these services can be achieved due to both the technical obstacles and time pressure in deploying a new technology. Beyond 5G networks are expected to enhance 5G capabilities towards the support of seamless wireless communication connectivity with reliable and latency guarantees. In the meantime, a multitude of mobile applications are emerging and gaining popularity, leading to a surge in computation demand. In general, the mobile devices are resource constrained due to the limited physical size. To mitigate burden from computation-intensive tasks with stringent ultra-reliability and low-latency requirements, multi-access edge computing is becoming one key technology by providing computation resource at the network edge. The trend of merging wireless communication and multi-access edge computing motivates the study of computation offloading in beyond 5G networks. The integration of multi-access edge computing into beyond 5G networks hold the potential of improving computation performance for mobile terminals. In such system, a mobile terminal decides whether the computation should be processed locally or offloaded to the edge computing server for remote execution. The design of computation offloading policy remains challenging. Basically, the performance of computation offloading is predominantly bounded by wireless communication between a mobile terminal and the edge computing server, and remote execution at edge computing servers. The wireless communication is performed by established link with an edge computing server, controlling the input data size of the computation task to be offloaded, and selecting the frequency and transmit power. For remote execution, task scheduling and resource allocation are essential for computing efficiency. When accounting for the uncertainties and randomness from the network, the computation offloading policy design becomes even more challenging. So to address the technical challenges listed in previous slide, we will develop a distributed learning framework based on machine learning to solve the optimal computation offloading policy. There are three types of machine learning, that is supervised learning, unsupervised learning, and reinforcement learning. The distributed learning framework we develop will leverage these advances in not only reinforcement learning but also supervised learning. In the literature, there exists a number of related works on centralized reinforcement learning for computation offloading. However, the centralized decision-making limits scalability of most centralized reinforcement learning approaches. Moreover, the information exchange between the central decision maker and mobile terminals in the networks incurs huge overhead. When there are multiple decision makers in a multi-access edge computing system, the degree of cooperation plays a vital role in the design of computation offloading policies. We therefore apply a multi-agent Markov decision process to formulate problem of computation offloading in beyond 5G networks, where each mobile terminal is regarded as an agent. More specifically, at each time point of observation, the system is in a global state which is accumulated over the local states at all the agents. And with the computation offloading policy, each agent takes a local action, which is a decision making in terms of a vector of computation offloading parameters. The system responds by moving to a new global state according to the probability distribution and sending back feedbacks to the agents. The feedback associated with each agent is the reward or cost signal, which is used to evaluate immediate effect of a joint action on the global state. The goal of each agent is to solve a policy which specifies the optimal local actions in different global states so as to optimize long-term feedbacks. For the definition of a multi-agent Markov decision process, solving an optimal policy for agents mainly lies in the state information sharing, the policy profile for other agents, identifying feedback, and knowledge of global state transition probability. Reinforcement learning technique can be explored to learn the optimal policy without any knowledge of the global state transition probability. However, on the one hand, the feasibility of full state information sharing among the mobile terminal is not obvious due to the large-scale deployments of a beyond 5G network. On the other hand, the formulation of feedback received at each mobile terminal from the multi-access edge computing system can be generally based on a combination of the consumed energy and experience latency, which is based on the joint action from all mobile terminals. Due to the sharing nature of communication and computation resources, the local action from different mobile terminals are coupled. With the complete cooperation among the agents, the overhead from inter-agent communication is overwhelming and prohibits the autonomous decision-making by each agent. Without any cooperation, the local action by each agent based on only the local state information can be suboptimal. The context information allows a mobile terminal to behave in a distributed and autonomous manner. So we introduce here a novel categorization of the context information, that is, conjecture, abstraction, and prediction. Each mobile terminal is capable of forming and updating conjectures on the behavior of other mobile terminals with proactively retrieved cumulative distribution information of the historical decision-makings from the centralized network controller, such as a base station. The received feedback of a mobile terminal is related to a specific joint decision-making in a specific global state. The classification of the feedback value into a finite number of intervals is equivalent to the abstraction of local states of other mobile terminals with bounded regrets. To exploit site information in computation offloading from the past, a recurrent neural network architecture can be incorporated into the decision engine of each mobile terminal for an accurate prediction of the global state at each time point. In the distributed learning framework, each mobile terminal learns the optimal policy with only the local observations and does not rely on state information sharing with other mobile terminals. The local observation made by a mobile terminal at each time point is composed of the local state and accessible context information. In most practical multi-access edge computing systems, each mobile terminal still faces obstacles from the explosion of local observation and decision-making spaces. Next, we will present some preliminary results to show the potential of the distributed learning framework. In computation offloading, one interesting question is how to adjust the radio resources between communication and computation services. The resource orchestration is particularly challenging when taking into account dynamics in beyond 5G networks. We apply an online reinforcement learning approach under the distributed learning framework for the resource orchestration in computation offloading. Here we list our two recently related publications for your references. We assume that a network operator implements a beyond 5G networks where the radio access network is connected to a resource-rich edge computing server. The radio access network sharing allows multiple wireless service providers to serve their respective mobile terminals. At each time point, the wireless service providers compete with each other for the limited frequency band from the network operator on behalf of the mobile terminals. All mobile terminals move across the discrete time in the service region covered by the radio access network according to a Markov mobility model. At each time point, the data packet and the number of computation tasks randomly arrive at each mobile terminal. The data packet gets queued until transmission, while the arrived task must be computed during the constant time interval between two consecutive time points. If being granted a frequency band from the band computation among the wireless service provider, a mobile terminal proceeds to decide the number of data packets scheduled for transmission and the number of computation tasks to be offloaded to the edge computing service. When the total number of data packet arrival exceeds the queen size limit, overflow happens, resulting in packet jobs. The remaining tasks arrive at mobile terminal are processed by the local central processing unit. The target of each service provider is to design a control policy which optimizes the decision-making of frequency band computation, data packet scheduling, and computation task offloading for mobile terminals under the global network state across the discrete time, such that long-term payoff is maximized. Gamma is the discount factor, ST is the global network state, FGT is the payoff, while mu k is the weight, the immediate utility UK of a mobile terminal K is a reward signal of realized transmit energy consumption, local CPU energy consumption, queen size, and packet jobs after joint action being performed under the global network state. PJT is the payment to the network operator for frequency band utilization. The coupling in decision making and the sharing of limited frequency band among the wireless service provider makes the solving of an optimal control policy extremely hard. We propose an online distributed multi-agent reinforcement learning approach which enables each wireless service provider to independently learn the optimal control policy. The flowchart of the online distributed reinforcement learning approach for communication and computation resource orchestration is shown in figure. More specifically, we replace the local states of all wireless service providers with the abstraction from the payment value classifications. By doing so, the original multi-agent Markov decision process is transformed into a single-agent Markov decision process, where the local observation at each time point includes the local state information and abstraction. For the purpose of reducing the dimensionality of the decision making by each wireless service provider, we further linearly decompose the single-agent Markov decision process into a series of simpler single-agent Markov decision process. The linear decomposition brings the advantage of letting mobile terminal to make local decisions of data packet scheduling and computation task offloading, while the wireless service provider is only responsible for frequency band computation. UJCJ can be learned using the traditional reinforcement learning. To address massive local state space and unknown statistical network dynamics of each mobile terminal, we use deep Q-learning to approach UKSK. We evaluate performance from the distributed reinforcement learning approach using numerical experiments. This table shows the key simulation setting. The first experiment is regarding the convergence performance during the approach training. The numbers of task arrival are random integers, less than 6 across the time points. The data arrival rate of the communication service for each mobile terminal is fixed to be 1.8 Mbps. The curve showed the variations in the long-term payment for a wireless service provider and the loss for a mobile terminal from updating the abstraction statics and deep neural network parameters. We can see that the convergence requires around 13,000 time points. In second experiment, we changed the data arrival rates and displayed the average performance of our approach at two baselines. In channel 1, the network operator allocates frequency band to the mobile terminal according to the channel gain information. The priority of each mobile terminal is to transmit as many data packets as possible. In Queen Well, the wireless service provider competed for the frequency bands in order to minimize the queen length and packet job for mobile terminals. We can observe that as communication traffic load increases, both the average queen length and the average number of packet jobs increase, while the mobile terminal consumes more transmit energy on average for data packet transmission. Compared to the channel wire baseline, there exists a higher probability for a mobile terminal to be allocated frequency band for transmitting data packets and offloading computation tasks when employing Queen wire baseline. On the contrary, to reduce packet job by more data packet transmission, our approach leaves more computation tasks to be locally processed, leading to an increase in average local CPU energy consumption. Overall, our approach achieves better average utility performance. lent to baselines. Let's make a brief summary of this work. In this work, we see that multi-agent Markov decision process can be adopted to model the problem of resource orchestration in multi-access edge computing. Distributed reinforcement learning approach enabled the wide service provider to behave independently without the statistic of network dynamics. Linear decomposition reduces the action of the problem is with a desired structure. When the state space becomes extremely large, deep reinforcement learning shows the power. Here is another related work. In this work, we propose a novel deep reinforcement learning approach to solve the problem of information freshness-aware computation offloading in an air-ground integrated edge computing system. Due to time limitation, I'm not going to expand discussion. Let's conclude this presentation. For computation offloading in beyond 5G networks, we developed a distributed learning framework to address the dynamic uncertainties and the sharing of communication as well as computation resources. For the experiments in the use case study, we also find that one important issue that prevents practical implementation of the distributed learning framework is the time cost in the training, for which the convergence of the online learning approach is expensive. We list here interesting research directions that deserve further investigation. First, off-party learning approach development. The distributed reinforcement learning approach requires online interaction with the network elements, which is the main reason slowing the approach training process. For mobile terminal, the learning approach training aims at finding an optimal probability match between a state and actions. To minimize the training cost, one idea is to develop the off-party learning approach that utilizes pre-collected online interaction data for the offline training. Second, transfer learning for training acceleration. The training of learning approach can be potentially enhanced if the historical learning experience can be leveraged. When communication and computation requests from the network exhibit significantly spatial and temporal correlations, transferring the parameter of a converged learning approach among mobile terminal dramatically speeds up the training process. Third, heterogeneity among the mobile terminals. For large-scale, for beyond 5G network deployments, there exists heterogeneity among mobile terminals in their communication as well as computation capabilities and context information availability. These heterogeneities have severe impact on the stability of the training process if all the mobile terminals simultaneously learn the computation offloading policies. Thank you for your patience.
Hello everyone, my name is Duanpeng Song. I come from Zhengzhou University in China. Thank you for giving me the chance to show my work, a lightweight deep learning algorithm for identity recognition. I will introduce my paper from 4 experts. Introduction. Architecture for our models, experiments, and evaluation and conclusion. Let's look at the first part. There are mainly 3 kinds of identity recognition techniques: computer vision, spatial sensors, and wireless sensing technique. Computer vision technique has high recognition accuracy and wide application range, but its shortcomings are obvious, which is easily affected by illumination and obstacle, invasion of user privacy. Spatial sensor technique use spatial sensors or wearable device to collect relevant human actions, such realizing humans' active perception. They can realize finite active perception with high accuracy, but these sensors need to be either highly sensitive and accurately located or owned by the monitored target. In recent years, identity recognition has been well researched. Different from the traditional biometric used for identity recognition, such as fingerprint and iris. Gait has attracted extensive attention due to the unique characteristic of long distance, non-contact, and not easy to disguise and so on. The main contributions of these papers are summarized as follows. We propose that the organized CSI data from Wi-Fi signals can be reconstructed and used for individual gait recognition. We propose a Bloom machines to make the network model of BitNet consume less storage and operation resource. We establish a dataset based on Wi-Fi signal for gait identification. Wi-Fi device collect gait data from volunteers of different genders, ages, heights, and weights. In order to evaluate the performance of BitNet, we conduct extensive experiments under various parameter setting. Experimental results show that the sensors achieved improved performance, particularly the identification accuracy of the system with a group of 50 people reaches 98.8%, which significantly reduced the number of participants and training time compared with conventional models. The second part introduces the BitNet architectures. The figure shows the architecture of net structure, including data processing models, deep feature extraction models and classification models, data collecting models. The system establishes a Wi-Fi monitoring environment through a transmitter and a receiver, which collects CSI data from different volunteers in the area. Data processing models responsible for converting the raw CSI data into a frequency energy map for pre-processing. Bloomberg. The Bloomberg established the relationship model between identity and CSI amplitude change classification models. According to different frequencies, energy maps corresponding to different volunteers, the neural network is trained. The third part introduces experiment and model evaluation. First of all, the related counters of data collections are introduced. We use TP-Link AC1750 wireless router as a transmitter and a desktop computer equipped with an Intel 5300 802.11n Wi-Fi NIC as a receiver. Receiver has 3 antennas, each receiving 30 subcarriers, so the amplitude established from the raw CSI is 90 dimensions. We collect data from Ample Laboratory. 15 volunteers was invited in the improvement, and each volunteer worked during 5 seconds and repeated the working 80 times. In this paper, we use occurrence per session record and FE scores as experimental measures. In order to explore the influence of different review channels on the experiment result, we designed 2 different review channels, namely a source link channel and a follow link channel. It can be seen from the figure 8 that both the source link channel and the follow link channel can maintain small model size. Moreover, with the increase of network layers, the accuracy of the follow link channel case is better than that of the source link channel case, but with a higher increasing rate. To verify the effects of channel compressions on model size and occurrences, we took a 3-layer Boolean network as an example, and the number of the neurons in each layers of convolutional operations was set to 32, 64, and 128. In order to verify the good performance of our VANET model, we compare the results of other models by accuracy, precision, recall, and FE scores, as shown in Figure 9 and Table 2. It can be seen from the table and figure that VANET model has better performance. It's this and this. In the last part, the following is a summary of our work. Facing the challenges of long training time, large computation, and poor performance of traditional deep neural networks, we designed a compact neural network to identify CSI of different individuals. Compared with the state-of-the-art deep learning methods for gait recognition, the proposed approach has higher recognition rate and operational efficiency. VANET gets rid of the dependence of hard-code features and relies end-to-end identity recognition. Future work will be based on VANET and combine the ideas of trace learning and investigate a generalized model for different indoor environments. My introduction is over. Thank you.
Hello everybody, my name is Banno and I'm going to be representing this paper called Bottleneck Feature Extraction-Based Deep Neural Network Model for Facial Recognition. This paper we have worked together with Banno Arnold, Kaping Yu, Yan Yang, Chao Jihua, Zhang Wen, Anup Kumar under the supervision of Mr. Ma Tian. Now, in this paper's research interest areas, we have a lot of things. For example, we have facial expressions using VGG16. We have deep neural networks, which were represented by DNA. Then we have convolution networks, which were represented by CNN. That is just number one. Then on number two, we are interested in logistic regression. And then the number three is k-nearest neighbor. Now, on the other side, maybe the question would be, why do we call it bottleneck? Now, in such cases, our algorithm is a combination of the best features in some of the best algorithms out there to get the best results. So that is why we call it a bottleneck. The best parts or the best features in most of the other algorithms which you combine together to come up with the best results. That is why we call it the bottleneck method. Now, the question might be, what are the problems you're trying to focus on? Well, number one, we were trying to identify facial features from random pictures. Now, the features tell us what the expressions are. Now, number two, we wanted to understand the effectiveness of transfer learning. Then we had to understand KNN and logistic regression methods and how they can improve facial detection techniques. Facial features detection techniques, that will be the right word. Then number four is the purpose of hard features. How can we take it to the next level? What else can we do with that? So that is basically what we focused on. In the facial detection methods, let us first define what detection means. There are mainly two words that mainly confuse so many people, but includes students and researchers at the same time. We have what we call classification, and then maybe recognition, or what we would call detection. Now, in classification, we know that we have two classes, or maybe we have two targets, right? And many maybe different features. Now, how do we group those? How do we classify those? How do we group them? So classification is mainly about grouping the data in the data set into different categories or groups, all right? Then detection or maybe recognition is the outcome that you get after you have classified something. All right. Now, in such a case, in our paper, we basically use the hard cascade method algorithm. Now, what does the hard cascade method do? The hard cascade method is mainly getting the dark and then you subtract off the white. You know that any picture, we are dealing with pixels mainly, all right? So when you're dealing with pixels, we have to first convert them into the grayscale, all right? Then into the grayscale, we have a range which goes from 0 to 1. Now, 0 most probably represents the black and then the 1 represents the white. So we know that in between 0 to 1, there are some figures. Now, every pixel you get, for example, if I get a 0.4, how do I calibrate that? Like, which side does it fall? Does it fall on the 0 side or does it fall on the 1 side? So I find out that 0.5 is more central. So I realize that 0.4 belongs on the 0 side. So I will consider that as a black. That is why we use this. So we go on breaking this down. In this process, we also have to use what we call the integral image. When you do the integral image, what happens? Since you're dealing with pixels, when you're doing the integral image, it kind of cuts those pixels down into smaller pixels, which actually help us to classify the image a little bit or to classify the face a little bit faster. That is the major reason why the integral image was created. Now, just by looking at this picture, we realize that, if you know a person who has done art, any image becomes an image because of the influence of the light. And the light maybe, brings in the pixels. So you realize that even if for a real professional photographer or even an artist who draws pictures, when they're drawing a picture, what brings the picture to life is the black and the white. All right. So you know that in the areas where there are a little bit of faults, those places are usually darker. And where the light, those areas which are a little bit closer to the light source are usually lighter. This is what hard feature is based on. All right. It identifies those darker areas, and then when you're using hard, we basically have a sliding window. All right. So a sliding window if it sees an area, it can identify the eyes, it can identify the nose and the mouth. Now, we know that any living organism has those, but then how can it differentiate them from the others? These are some of the wonders of the HAR algorithm. If I got a face of a human being and a face of a dog, can I actually extract out the face of a human being using HAR? Absolutely. And this is why we use the HAR algorithm. And we use it to extract in case I have a picture, there is some noise in the background, or maybe some other things which are not a human face in the background. Is there any way how I could extract out just the faces in that picture? And it worked out actually in our algorithm. Until then, I've just been talking about the HAR features. Now, I said HAR features and integrate image kind of move hand in hand. So it's the same thing. I usually have to find out the nearest point that comes closer to 0 and 1. All right. I get the area which is black and the area which is white. I subtract those pixels. The number I get is what gives me the integral image. After that, when we extracted the face, now we have to put it to the next algorithm, right? Now we use the VGG16 algorithm, right? This is one of the most high performance algorithms out there, which was trained on the image set data set, which has almost like 4 million images. It achieved a 92.7% kind of success rate in its work. So what we do here, some of the things we have to realize is we have what we call filters. We have filters and we have what we consider as layers. So if you input an image, all right, now you put it through different layers. Now in these different layers, this image is being slimmed down. So in other words, I don't have to have a lot of pixels. I'm cutting down the pixels using the fully connected layer, using these layers, and then I put it to the connected layers, and then I get the output. Now, what does the VGG16 do? In others, it sizes down the images because if I'm having so many pixels, there are some pixels that are really not even useful. I trim them down a little bit to get the most meaningful pixels that I can use. That is why I need this algorithm. Now, why do I need it? It's because I want to limit the noise, first of all. So that is basically why we use the VGG16. Now, after the VGG16, one of the few algorithms we also utilized in that area was the transfer learning. Now, we know that transfer learning, basically, I do not need to retrain my dataset again, right? Because transfer learning itself, when you're using the VGG16, it's already pre-trained, right? Now, when I use the transfer learning, it means that I'm just gonna get the images I'm doing and I'm just gonna refer them to the already trained layer. So I don't have to retrain them again. I don't have to do so much the data collection. So what does this basically do? It reduces the work for me and for the machine as well. All right. So in transfer learning, what we basically used was we did not want to take more resources, but the aim was to get the better results. Right. And this took us to the deep convolution neural networks. Now, in these deep convolution neural networks, the main purpose was now, since we have got a data set that already has the images that, had our aim, can we find a way of using that data set to train this new data set without having to go out and collect other new images? And if we do that, is there any chance how we could get better results in identifying or in detecting which category we are talking about? Because what we're doing here, first of all, I forgot to say this in the first video, is classification problem which comes under supervised learning. So it means I already have the features, I already have the target, and now I need to train the machine to find out what exact target do I want. All right, so this is basically what we did. And in this case, using these algorithms, we were able to find out with the 6 basic if facial detection modes we used. Now, one of the questions that was raised was, why didn't we use why did we only choose 6, not 7? Yeah, the reason is, for example, if I'm having surprised and fear, sometimes it is difficult for even a human being to classify those. The facial expression at the time of capture of the image is very hard to differentiate that. So it would give, I would suggest that had I put it there, we would have got the same results, but I was more interested in the difference, so I didn't do that. The algorithm representation of our method, we called it the BFE model. This was the flow of the whole algorithm. First, we input the images. Then the next, we had to detect the face using the hard cascade method or the hard algorithm. Now we had to extract out the hard features using add-boost and then cascading. Then we put it to the next algorithm, which was to extract out the features, which was the VGG16. Then we put it through a deep neural network training model. Now, in the deep neural network training model had 6 dense layers. All right. Now, after we do that, when we put it in the deep training model, we got 6 expression classes. Which classes was surprised, there was being sad, there was being happy, there was being afraid, That's what we did. Then we upload it in the memory. Now, this is where the mobile part comes in. Some of the major problems we have today, in as much as cloud computing is doing a very, very wonderful job, the costs are a little bit also complex. Now, my suggestion is, how about if we find a way of classifying data or grouping data on a local level before we put it on the cloud, I think that saves costs, or it might even increase speed. It's one of those things that I think that if we applied them in the real world class scenario, it would work best. Okay. Now, when we do that, then we test the model. Now, we tested the model. First of all, we trained this model. We used 80% of the images we had to train the model, and then we used 20% to test the model. But like I said, we also use transfer learning. So basically, our training was not done by us; it was done by the transfer model. Using our method and using the KKK method, KKK method had a lot of good things, but it performed really, really bad in sadness, in anger, it also failed a little bit, all right? And that was it. Then when we go to the next one, which is the logistic regression. Now, logistic regression did better in sadness and in anger. It did better than the KNN. So I would say that logistic regression was, depending on our data set, was better than KNN. Then on our method, though, I would like to say that we did absolutely very good in surprise, in sadness, in happy, in disgust. In anger, I would suggest that the logistic regression did better than us. Then on neutral, we beat them. In the anger area, our method wasn't so good. Now, the question might be, okay, then why didn't you use other methods? Maybe why didn't you use this SVM? Yeah, I didn't use the SVM. I would love to publish another paper, though, using SVM. I think SVM would perform. I don't know whether it will beat this method, but I'll try to write it to publish a next paper using SVM and see what results I can get. In programming, when we go by the accuracy, because that is the main reason why these algorithms exist, the accuracy of our method was 98.59, then k-nearest neighbors was 83, then logistic regression was 89. But on the F measure, we were also doing good. Then the F measure, the other ones were not, KNN wasn't doing so good, but it doesn't mean I won't have to use it somewhere. I would have, it was doing good though. The code snippets now, I know maybe this one looked a little bit tiny, but these are images we just downloaded off the internet when we were testing our algorithm. But it was detecting like I said, the success rate was 98. Actually, these are random. We didn't even have to we didn't get something wrong when we were testing it. So if we continue testing it for a long time, it will keep getting better because this is machine learning. But this is what we got, and everything was being detected in the right way. Now, our main research interest maybe could be applying more methods. I want to see if we used the support vector machines could be a method. Maybe we could use support vector machines and then try to put in more, automate this. Maybe we can also take it in form of AI, or maybe we can use it in the videos, analyze the average if facial state or the facial detection state of a group of people in a video. That is research I would like to participate in, and if we can use this, maybe we can also find out the health problems in people. It might not be real health data, but psychological health is also health. Maybe we can use it in busting crime, because some organizations use videos to know who has committed a crime. I think if we can take this research to a higher level, maybe we could come up with answers to such questions. Thanks to everybody, and thanks to College of Computer Science, Xi'an University of Science and Technology, then Global and Telecommunication Institute, Waseda University, Shinjuku, Tokyo. Then thanks to Shenzhen Boy Technology Company, Computer School, Hebei University of Arts and Sciences, then School of Fundamental Science and Engineering, Waseda University, Tokyo, and Department of Electronics and Engineering, East West University, Dhaka. Thanks for everything, and thanks for all the members who have been a part of this research. We would like to answer some more questions if they are emailed to us. We're sorry we can't make it that side because of the pandemic, but we hope everybody has had a good time. And for any other questions or any references, please, I'll be open for any questions. Thank you very much.
Hello everyone, my name is Zhao Wang. I come from Zhengzhou University in China. Thank you for giving me a chance to show my work. Human activate recognition using MSHNet based on Wi-Fi CSI. I will introduce my paper from 4 aspects: introduction, architecture of our model, experiments and evaluation, and conclusion. Let's look at the first part. There are many three kinds of activate perception technologies: computer vision, spatial sensors, and wireless sensing technology. Computer vision technology has a high recognition accuracy and a wide application range, but its shortcomings are obvious, which is easily affected by illumination and obstacles, invasion of user privacy, and existence of blind spot. Spatial sensors technology uses spatial sensors or wearable devices to collect relevant human actions, thus realizing human activate perception. They can realize fine-grained activate perception with high accuracy, but their installation and maintenance usually require high cost. Therefore, preventing this technique to be widely used. Wireless sensing technology overcomes the shortcomings of the above-mentioned technologies and has gained increasing attention in recent years. It further consists of RF-based and Wi-Fi-based approaches. RF-based requires special equipment to be customized, and the cost is usually relatively high, so it is not suitable for large-scale installation. In recent years, with the widespread deployment of Wi-Fi hotspots, using Wi-Fi signals to implement some wireless sensing applications has attracted great attention of researchers. By utilizing the ubiquitous in-housing Wi-Fi signals, freeing the personnel from any onboard equipment, as well as avoiding the effect of illumination and unnecessary personnel prevents invasion. Initially, researchers realized indoor localization, gesture recognition, and simple motion detection based on received signal strength in Wi-Fi signals, because RSS contains to signal information to recognize fine-grained human activity. Channel state information has emerged to replace it. Channel state information is used to estimate channel attributes of communication links in orthogonal frequency division multiplexing technology. In the frequency domain, a wireless channel having a plurality of transmit and receive antennas is described as the equation where y, x, theta, and h represents the reception vector, transmission vector, noise vector, and channel matrix respectively. Channel matrix is the estimation of CSI. The main work of previous researches is to treat the collected CSI data as a whole, as shown in the red big circle above. In this paper, we aggregated the collected CSI data according to different antennas, as shown by the 3 small circles in the above figure. By randomly selecting and displaying the subcarriers of CSI data from different antennas, we can see that the subcarriers of CSI data from different antennas fluctuate differently in the right picture, which provides a basic for us to study the data from different tenors respectively. The second part introduces MSHNet architecture. Firstly, we collect CSI data related to human activity. Secondly, we extract the amplitude of CSI and process the data with time sliding window, and then aggregate the data from different tenors. Finally, we use our well-designed BLSTM-TCN deep neural network model to extract features from different aggregated data. In order to improve the performance of the model, we extract features from the whole data and then concatenate them with the extracted features, and then input them into softmax functions for classification. Finally, we apply the vote mechanism for getting the final result. BLSTM-TCN deep neural network is the core module in MSHNet, which uses bidirectional LSTM and temporal convolution network to extract the features of the input data and then concatenate the results of the two and output them. The third part introduces the experiment and the model evaluation. First of all, the related contents of data collections are introduced. We use TP-Link AC 1750 wireless router as the transmitter, and a desktop computer equipped with an Intel 5300802.11n Wi-Fi NIC as the receiver. The receiver has 3 antennas, each receiving 30 subcarriers, so the amplitude extracted from the raw CSI is 90 dimensions. We collect data from 4 environments, including standard data collection room, conference room, exhibition room, and psychological consultation room. 10 volunteers were invited in the experiment, and each volunteer collected 5 actions, namely no action, walk, run, and sit down, stand up, squat. Each action is repeated 80 times. In this paper, we use accuracy, precision, recall, and F1 circles as experimental metrics. In order to put forward a better model structure, we experimented with a variety of network structures, and the results are shown in Table 2. From the table, we can see that the MSHNet model structure has the best results, so we choose MSHNet as the final model structure in this paper. In order to verify the good performance of our MSHNet model, we compared the results of other models and made the confusion matrix as shown in Table 3 and Table 4. Table 5 shows the results of MSHNet model. It can be seen from the tables that MSHNet model has better performance. In order to verify the adaptability of MSHNet model in different environments, we collected data in standard data collection room, conference room, exhibition room, and psychological consolidation room and conducted model training respectively. The experimental results are shown in Figure 7 and Table 6, from which we can see that MSHNet model has better adaptability to environment. In the last part, we mainly summarize the main contributions and shortcomings of this article. Our main contributions are as follows. 1. We received the CSI by different attenders. 2. We proposed a deeper neural network model, MSHNet. 3. Our model is supervisor to some other excellent models. The existing disadvantages are that 1. The MSHNet model has good performance, but the model size is relatively large. 2. MSHNet is only for single person, so in future work, we will mainly study human activity monitoring in multi-person situations. 3. We did not use the phrase information of CSI, so we will study the relationship between phrase and the human activity in the future. 4. For multi-environment situations, we hope that the model trained in one environment can adapt it to other environments quickly. My introduction is over. Thank you.
Hello everyone, my name is Wu Fan. I'm the first author of this paper. It's my honor to be here to take this presentation. Here we go. The title of this paper is A Novel Neural Network Model for Demand Prediction of Bike Sharing. It will be divided into the following 5 parts. The first part is introduction, then neural network structure, learning rule, and demand prediction of bike sharing. Finally, we get the conclusions. With the development of sharing economy, bike sharing has become an important low-carbon travel way. At the same time, we can't ignore the fact that it also brings several social problems. For example, there are so huge number of bikes, we can even see them anywhere in our lives. Another problem. Sometimes we want to rent the bikes in the stations, but there is no bike. Sometimes we want to return the bikes to the stations, but it's full. It means the scheduling is belated. And the unreasonable distribution of bike sharing stations always causes the waste of social resources. From the perspective of lean production, this phenomena could be considered the waste of overproduction, waste of waiting, waste of inventory, and waste of transportation. What is the key problem? In our opinion, the distribution and scheduling of bike sharing is unscientific. But we think the deeper reason is imprecise demand prediction of bike sharing. The traditional prediction methods are mainly based on statistics. However, these methods have their own limitations, and there are some more advanced methods. They always use artificial intelligence technology, such as neural network. So, what is neural network? It is also called artificial neural network. It is an algorithmic model that simulates the characters of human brain and processes distributed information in parallel. According to the numbers of hidden layers, feed-forward neural network can be divided into the following 2 types. One is single hidden layer feed-forward neural network, and the other is multiple hidden layer feed-forward neural network. Different structures means different advantages and disadvantages. Simply speaking, for SLFN, it means simple structure and faster training speed, but its prediction accuracy is lower. For MLFN, the advantage is high prediction accuracy, but it means complicated structure, slow training speed, and low generalization. We are a little bit greedy. I want the advantages of these 2 neural network structures. So, we propose a novel structure called pseudo-double hidden layer feed-forward neural network with the following design consideration. The first is Multiple hidden layers can achieve high prediction accuracy, even by setting fewer nodes in each hidden layer. The second is, in the input layer, time series sample data may have some noise disturbance to some extent, and appropriate smooth process can reduce the influence of noise on the accuracy of final results. The structure of PDLFN is shown as follows. PDLFN includes input layer, hidden layers, and output layer. Compared with SLFN and MLFN, it has a V layer with one special neuron. This special neuron is no longer with bias and activation function in the traditional sense. It has its own function. We call it smooth function. The definition of smooth function is as follows. With this V layer, the data process of PDLFN is from samples to outputs. Denoted as the function FJOut. The learning rule of PDLFN is called IPSO-ELM. The influence of initial random biases and weights on prediction accuracy can be reduced by IPSO to optimize the initial thresholds and weights of ELM. So, improved particle swarm optimization in extreme learning machine is proposed as learning rule of PDLFN. Compared with the traditional PSO, the improvement proposed in this paper is mainly reflected in these two formulas. The coefficients of VIJT are adjusted to the self-adaptation versions. The learning process of IPSO-ELM is shown in this figure. We can use this model to predict the demand of bike sharing. The initial dataset is mainly from the official website of Divey Bike Sharing Station in Chicago, USA. Here is the figure of prediction model. The numbers of neurons in each layer from input layer to output layer are 3, 1, 29, and 1, respectively. In order to verify the performance of the improved particle swarm optimization algorithm proposed in this paper, the fitness evolution curves before and after the improvement are compared, shown in the following figure A and figure B. Here are the prediction results. The activation function set it in this neural network is sigmoid, and the smooth function is weighted moving average function. Here are the main conclusions. That's all. Thank you for listening.
Hello everyone, I'm Ryohei Banno from Kogakuin University, Japan. I'm very happy to have the opportunity to do this presentation in MONAMI 2020, and I wish to express my appreciation to the relevant people of this conference. Today, I'd like to talk about various trade-offs in IoT systems and our researches for tackling those trade-offs. To begin with, I'd like to mention the COVID-19. As you know, COVID-19 has significantly changed the world and our lives. It caused very hard situation, but the lives after COVID-19 have both positive aspects and negative aspects. For example of good things, remote work demand is significantly increased and it is enhancing the digital transformation. In addition, people have more personal time. On the other hand, many industries are suffering damage and our activities are quite limited, such as restrictions on watching sports. Personally, I am very worried about the Olympic Games in Tokyo, which is planned to held next year. For the MONAMI 2020 participants, it is one of the positive aspects that we can participate in this conference reasonably. I mean, no need of travel expenses, but a negative aspect is that we cannot discuss face-to-face in Chiba. By the way, Chiba is very good city and I hope you to have future opportunities visiting there. Now, let's get down to the subject of this presentation. IoT systems provide valuable services by utilizing connected things. IoT systems are basically greedy, namely, they have various requirements such as capability of many users, quick response of processing, and so on. The solution for each requirement has pros and cons, like the new normal by COVID-19. Some solutions could conflict and lead to various trade-offs. In this talk, I'd like to mention these 4 trade-offs in IoT systems. The first one is the trade-off between the cooperativity and the flexibility. IoT systems literally need cooperation among various kinds of computers, such as smart devices and cloud servers. To do so, we can use communication protocols like HTTP. It goes without saying that such collaboration makes value. However, if you build the system with tightly coupling all of the components, it causes the difficulty to change the system architecture. That is, if users want to add a new kind of IoT devices, or a service provider wants to change their server computer, it's not easy to do so. From such viewpoints, IoT systems need themselves changeable, since the IoT-related technologies are rapidly advancing. Systems with less cooperation have flexibility to change, but obviously, limited cooperation can provide limited functionalities. One of the solutions for this trade-off is using publish-subscribe messaging model. Different from typical communication ways like using HTTP protocol, it uses an intermediate server called a broker. A receiver is called a subscriber, and it subscribes to the broker by specifying their interest. The broker forwards messages from publishers to appropriate subscribers. The most known pattern is topic-based publish-subscribe model. In this model, publishers send messages to topics and subscribers subscribe to topics of interest. By using publish-subscribe communication model, clients can communicate with each other but without directly knowing each other. It means that it enables cooperation in a loosely coupled manner. Now, let's proceed to the second trade-off, loose coupling and performance. As I said, publish-subscribe model is advantageous in loose couplingness, but disadvantageous in performance due to load concentration on the broker. Especially when considering a cloud broker that is to realize cooperation of devices over a wide area, heavy communication load is concentrated on the broker and it becomes a bottleneck. To tackle with this issue, we've proposed a distributed publish-subscribe architecture that uses edge brokers. We assume that multiple brokers are placed at the network edge and publishers and subscribers connect to the closest broker. Brokers share published messages with skip graph algorithm that enables cooperation without single point of failure. Skip graph is one of the algorithms of peer-to-peer systems. In skip graph, each node has a key, for example, integer, string, and so on. Important characteristic is that each node can issue a range query. Issued queries are delivered to nodes whose keys are included in the range. Skip graph has a hierarchical structure. Level 0 is a doubly linked list of all nodes sorted by keys. In skip graph, each node also has a random sequence called membership vector. Each node composes a doubly linked list with nodes whose membership vectors have the same first I digit in level I. For example, node A has a membership vector of 001, so node A connects to node C in level 1 because the first digit of node C is 0. Delivery process of skip graph starts from the maximum level of the node. For example, when node A issues a message towards the key 275, the message is forwarded skipping long distance at the higher level and gradually moves down to level 0. Eventually, the list of level 0 ensures the reachability. The path length of forwarding queries is logarithmic order of n participants, while the size of the routing table that each node must have is also logarithmic order of n. In our proposed method of the distributed publish-subscribe architecture, we use skip graph for the cooperation among brokers. As an assumption, each node, namely each broker, possesses the topic names of interest as a subscriber or a publisher. That is, each node has two kinds of parameter, topic name and node type. In the proposed method, we use the topic names and the types of nodes as keys and constructing skip graph. Nodes are sorted by names and types in that order of precedence. Such a totally ordered relation is possible by adding specific suffixes to topic names. For example, a node joining topic T1 as publisher has a key of T1 pub. As a result, the units of every topic are sorted at level 0, and inside the topic units, the units of every type are also sorted. Publishers can deliver messages to subscribers by using range query function of skip graph, like this. The path length is logarithmic order of the sum of the number of publishers and subscribers of the corresponding topic. These skip graph-based distributed brokers can provide effective load distribution, especially when a topic has high locality, namely when all publishers and subscribers are under the same broker. Messages related to that topic do not apply a load on other brokers. Next is the trade-off between throughput and latency. As I said, the distributed edge brokers can provide load distribution. It means that high throughput can be achieved compared to a single cloud broker. On the other hand, cooperation overhead among brokers could increase the latency. In the proposed method, messages are forwarded in multi-hop manner and it leads to larger latency. Indeed, this figure indicates the result of an experiment comparing the latency and the throughput between the single broker case and the 5 brokers case. The cooperation among 5 brokers results in 3 times higher throughput compared to a single broker, whereas the latency increases to approximately 6 times larger. Such increase of latency is undesirable for real-time applications. To overcome this issue, we've proposed a method to construct an adaptive topology to obtain both high throughput and low latency. The idea is to adaptively compose a full mesh topology for a small topic while a multi-hop topology for a large topic. Multi-hop topology is advantageous in load distribution but disadvantageous in latency. If the number of nodes participating in the topic is small, there is less need of load distribution and we can avoid latency increase by composing full mesh topology. In the proposed method, each publisher of a topic adaptively maintains additional links to subscribers by using a methodology called flexible routing tables. Only when the number of subscribers is small, the additional links are held. For example, this link of dotted line does not exist in the previous skip graph-based method. When the number of subscribers is small, each publisher adaptively adds such links to its routing table, and consequently, a full mesh topology is composed. Here is a result of simulation experiments. From this result, when using a single broker, latency increases linearly according to the number of subscribers, like this. Existing methods achieve lower latency than the single broker for many subscribers, but higher latency for few subscribers. Regarding our proposed method, it achieves good performance similar to the single broker for few subscribers, as well as good scalability like existing methods for many subscribers. The last topic is a trade-off between the heterogeneity and the development cost. Considering to deploy distributed edge brokers, heterogeneity of edge environment could be an issue. That is, an appropriate broker product is different according to the environments. Using a single kind of broker could cause problems such as performance inefficiencies. However, developing suitable products for all environments takes a huge cost. Regarding this issue, we focus on the MQTT protocol. MQTT is a Layer 7 protocol for topic-based publish-subscribe messaging. It is recently well known for the use in IoT systems due to its lightweight protocol design and useful functions. To address the issue of the trade-off between optimization in heterogeneity and development cost, we've proposed the interworking layer of distributed MQTT brokers. We call it ILDM. Supposing there are multiple brokers and clients, an ILDM node is placed between a broker and clients like this. An ILDM node basically behaves as if it were a proxy and relates MQTT clients and a broker. In addition, it can connect with other ILDM nodes so that brokers can cooperate with each other via ILDM nodes. The important point is that brokers need not any specific function for the cooperation. There could be various cooperation algorithms. ILDM has APIs inside it to easily implement the cooperation algorithms. By using ILDM, we can make arbitrary kinds of brokers to cooperate with each other. This means that we can utilize various existing products, including open source softwares, for the distributed publish-subscribe architecture. Here is a result of experiments. We implemented two simple cooperation algorithms named PF and SF. I omit the detail in this talk, so please refer to my paper for more detail. This figure indicates the throughput comparison. There are 5 patterns. Pattern A is the case using a single broker without ILDM, whereas pattern B is the case using a single broker with ILDM. Patterns C, D, and E are using 5 brokers with ILDM. It is confirmed that ILDM-based distributed brokers will work and it can improve the throughput. This is just for your information, but we recently created a tool named MQTT Loader. MQTT Loader is a load testing tool for MQTT brokers. It generates multiple publishers and subscribers and applies load on a broker. It supports the newest version of MQTT protocol, version 5. MQTT Loader is easy to use and you can configure various parameters such as the number of publishers. If you want to quickly test this tool, the mandatory parameter is only the broker IP address. Here is a sample movie to run MQTT Loader. You can run it by specifying the broker IP address like this. Then it generates multiple publishers and subscribers and communicates with the broker. After completing to send and receive messages, it automatically calculates statistic data. Here is the throughput between publishers and broker. And here is the throughput between broker and subscribers. And here is the latency between publishers and subscribers. It would be appreciated if you use it and give us feedback. It is publicly available on GitHub. Now I'd like to conclude my talk. There are various trade-offs in IoT systems. Publish-subscribe messaging model is one of the solutions to address the trade-off between cooperativity and flexibility. Our research group has focused on it and tackled the three trade-offs: loose coupling versus performance, and throughput versus latency, and heterogeneity versus development cost. There are lots of requirements in IoT systems, and some of them are hard to combine, but I think this is very the point we should challenge. We will further advance our research to realize future valuable Internet of Things. That's all, and thank you very much for your attention.
Hello everyone, I'm here to give an oral presentation. The title of this paper is Resource Allocation Scheme Design in Power Wireless Heterogeneous Networks, Considering Load Balance. My presentation contains the following 5 parts: Introduction, System Model and Problem Formulation, Proposed Algorithm, Simulation Results and Discussion, Conclusion. First, it is the introduction part. Smart grid is a new generation of transmission and distribution systems that have emerged in recent years. In heterogeneous smart grids, mobile network traffic and various power interconnection services grew in a high way. How to deal with uplink content transmission is one of the key issues to alleviate the high load of smart grids. Catching the service at the edge of the smart grid network is a common optimization method to reduce the heavy network traffic. By catching the content of the core network at the edge of the mobile network, users can obtain the required content at the base station close to the user equipment. In this paper, we propose a cooperative resource allocation scheme in heterogeneous smart grid networks. Firstly, the effect of computing and channel resources on the initial latency of the electric services is studied. Secondly, the model of topology and resource distribution in the network is established, with the goal of minimizing the overall network delay. Thirdly, an algorithm combining KM matching and genetic algorithm is proposed to solve the proposed problem. Finally, the simulation results show that the proposed algorithm optimizes the average delay of the smart grid service. Next, I will introduce the system model and problem formulation. This paper considers that in a small grid network, as shown in Figure 1, G-small base stations are divided into a maximum of I clusters by overlapping clustering to provide services for I users. In mobile video services, high-quality versions of the same video can be converted to low-quality versions through transcoding. In this way, users' requests for different versions of the same video can be met by combining higher version videos with video transcoding. Then, I will give some assumptions. Firstly, each base station occupies a different frequency band range, and different users are allocated different sub-carriers for communication. Secondly, the transmission power of each base station in the network is the same. Thirdly, during the transmission period, it is assumed that the location of user remains unchanged. In a small grid network, when a user is served by only one base station G, for each user I, the delay from its request for a specialized content to the start of playing the video is merely composed of the calculated delay and the communication delay. The time required for video transcoding at the base station is related to the total amount of computing tasks and the allocated computing resources. The total amount of calculation tasks can be expressed as the product of the difference between the video bitrate before and after transcoding and the video length. The communication delay includes 2 parts, which are the uplink, offloading, and downlink transmission, respectively. Assume that the user has sufficient storage space for video caching. Among them, the frequencies between base stations are different, and each base station allocates its own channel bandwidth to different users according to frequency bands. Therefore, without considering path loss and mutual interference between users in the network, the base stations cooperate in a manner of overlapping clusters. The connection relationship between each user and the base stations is represented by X. Then the minimum average waiting delay of users in the network is as follows. Constraint 1 indicates that the quality of the version of the video cached at the base station should be higher than the quality of the video requested by the user in the overlapping clusters, so that the high-level video can be converted to the low-level through video transcoding. Constraint 2 indicates that the number of users connected to each base station should not exceed the maximum number of access users. Constraints 3 and 4 respectively indicate that the bandwidth allocated by the base station and the computing resources should not exceed the total amount of resources at the base station. Third part, we will introduce the proposed algorithm. The optimization problem is decomposed into two sub-problems. Problem 1, the overlapping clustering problem. The improved KM algorithm is used to match the user and the base station to find the anchor node of the overlapping cluster. Problem 2, the resource allocation problem. This paper uses the genetic algorithm to allocate the channel resources and computing resources of the base station. The algorithm proposed in this paper merely includes two paths, KM algorithm for base station grouping and the genetic algorithm for resource allocation. The process of the algorithm is shown in the following table. The traditional KM algorithm needs to be improved to adapt it to the needs of special scenarios. Since the grouping method in this paper is overlapping clustering, in order to ensure the quality of service of users, at least one node needs to be allocated for users. After forming a group, a node is also needed in the group to collect the distributor user information. This node is called an anchor node. In the overlapping clustering problem, a key problem is to find a one-to-one match in the network topologies, so that each user owns an anchor node. In particular, in the time delay problem in this paper, it is necessary to ensure that the user's time delay is the smallest in the subgraph formed after the one-to-one matching. Since the KM algorithm is essentially a process of continuously relaxing restrictions and finding the best match through the Hungarian algorithm, when the number of base station nodes is greater than the number of user nodes, the KM algorithm can also be used to slow. Different from the traditional method, the KM algorithm in this paper will stop when the user equipment finds a matching base station. After slowing the grouping method in the resource allocation problem, this paper finds a solution through genetic algorithm. Next, It is simulation results and discussion part. As shown in Figure 2, when the number of users increases, the delay of each algorithm increases. The overlapping clustering algorithm proposed in this paper can optimize the overall performance according to the actual situation. As can be seen from Figure 3, with the increase of frequency band resources, the delay of the algorithm generally decreases. The overlapping clustering algorithm proposed in this paper has the least impact on the total delay when the frequency band resources are small, so it shows certain advantages. As shown in Figure 4, with the reduction of computing resources, the amount of resources that can be used for transcoding in the two multiplayer packet algorithm is reduced, which has a greater impact on the final delay performance. However, the resources allocation algorithm proposed in this paper still has certain performance advantages. Finally, I make a conclusion of this paper. This paper proposes a resource allocation algorithm based on overlapping clustering for transcoding and distribution of multi-version video. This article considers the optimization problem in two phases. Firstly, the KM matching algorithm is used to select the anchor node corresponding to the user, and the overlapping cluster is completed. The second stage uses the genetic algorithm to allocate resources within a group to achieve global optimization. The simulation results show that the algorithm has good delay performance in the video transcoding distribution of small base stations, especially in the scenarios with less resources. That's all, thank you.
Hello everyone, this is Sanas from UEC, and I am glad to be here to make this presentation about Virtual Edge collaborative computation offloading in VANET. Here is outline of this presentation. In this section 1, we will introduce the background. Then we talk about our system architecture. Next, in section 3, we will formulate the equation for our system model. In this section 4, we use the simulation to evaluate proposed scheme. At last, we will conclude our work. First of all is background, and in this section, I will introduce the background of my work, motivation, and related works. What is edge computing? The definition from Wiki. Edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed. To improve response time and save bandwidth. What are the advantages of edge computing? The advantages are listed below. Low latency, scalability, reliability, efficiency, privacy, and security. Here, among these characteristics related our research is low latency. What is VANET? The definition from Wiki. Vehicular ad hoc network referred to as VANET. It is evolved from mobile ad hoc network, vehicle-to-vehicle ad hoc mobile communication and networking application, where network can be formed and the information can be relayed among vehicles. The application of smart automobile in the VANET, such as intelligent vehicle control, traffic management, and interactive application, require significant computation resource. Some studies consider that service can be finished at the cloud or mobile edge computing. So do this. It can elevate the problem of response shortage at the node or vehicle. However, due to high mobility, vehicle in transit may pass through several RSU or MEC server during the task offloading process. And second, the dynamic topology changes caused by the mobility of vehicular make offloading transmission complex. The following part is our motivation. The tasks are offloaded to vehicle with available computing resource through DSRC technology such as IEEE 11P to finish the execution. Our aim is, first, vehicle with available resource at the vicinity can be established as a cluster, named as virtual edge, and then the task is offloaded to the member of virtual edge. Second, to improve the stability of link between vehicles. Last, to avoid migration between nodes frequently. Section 2 is system architecture. The architecture added a layer based on the mobile cloud computing architecture, which has 3 layers: cloud layers, fog or MEC layers, virtual edge. Virtual edge is established by vehicle node to explore lower cost resource when the computational resource provided from BIS or RSU did not satisfy the constraint. The proposed architecture is very suitable for dense vehicle scenario, such as urban area and can utilize the computational resource of parked vehicle and other running the same direction. Without modifying the cloud and fog or edge layer, virtual edge can be used as a complementary to expand the function of utilizing resources in vicinity. A task needed to be sent to the cloud when the task cannot be completed at BS or RSU or virtual edge. Here is section 3. In this section, we will introduce system model and problem formulation. Experimental scenarios described in below. All vehicle moved on the street road by random velocity. Every vehicle equipped with the device which receive and send the message over IEEE 11P. Every vehicle broadcast BSM in the interval to exchange the vehicle information such as velocity, acceleration, and minima. Every vehicle connected each other directly if they are in the communication range. Then here is motion model. Due to the mobility of IOV, establishing a stable virtual edge faces great challenges. In order to return to the result of computation offloading before connection between vehicles are broken, the prediction of virtual edge duration time becomes very important. In the paper, we developed a simple model, quadratic equation. This motion model used to prediction for vehicle mobility. The subsequent comparison shows that the performance of model with motion prediction is better than other schemes. In the perspective of communication model, IEEE 11P and TCP used as the data transmission protocol. Computation model formulated by the following equation, where DJ refers to CPU cycle of block J, Fi refers to CPU frequency of node I. Then the execution time of task modeled by following equation. Utility function modeled formulated by following equation. The first item is virtual edge duration time, and the second item is task execution time. The first constraint guarantees that the result can be returned to vehicle. The second constraint guarantees that the member of virtual edge did not disconnect frequently. Here is section 4. In this section, we will introduce the performance evaluation. At first, we show that the parameter used in the simulation. Here, simulation time is 320 seconds, so the total execution time is 120 seconds. Similar we used is WINS 4.7. Four methods were developed for comparison to our proposed scheme. First is random scheme. This scheme is randomly select vehicle within one hop communication range. Second is minimum distance first scheme, setting a higher priority for the vehicle with the minimum distance to master vehicle. Next one is maximum available resource first scheme. And the last one is longest drive-through time first scheme. In this scheme, we considered motion model to predict the vehicle mobility. It enhanced stability of vehicle link and decreased switching time between vehicles. Due to the continuity of cloud service, virtual edge topology changes is required in order to satisfy the requested service. The virtual edge will be invalid when a member leaves the communication range of master node. At this time, the master node automatically maintains virtual edge, resulting in the change of virtual edge members. The following two figures show that duration time of virtual edge and available computational resource when virtual edge is established without maintenance. Figure in the left show that the duration time of virtual edge becomes shorter when the number of virtual edge members reduce. In the similar way, computational power is enhanced when the number of virtual edge members increase. However, with the decrease of duration time, the ability to supply continuous computational capability will drop down. Then two figures show that duration time of virtual edge and the number of unexpected disconnection when virtual edge is established with maintenance. Red line is our proposed scheme, better than other schemes. The figure in the right, unexpected disconnection is caused by the following reason. First is member node leaves the communication range of the master. Second is the failure to receive BSM due to packet losses. Unexpected disconnection during the execution is harmful to collaborative offloading tasks. It is very important that maximum computational capability by increasing the number of slave nodes to minimum the number of unexpected disconnection. It can be seen from right figure. Virtual edge with 6-member node makes the largest computational resources and has the smallest unexpected disconnection. Next, two figures present that number of the virtual edge reformation failures and the available computational capability of virtual edge. The figure in the left show that virtual edge recreation fault due to the difficulty in finding the enough vehicle at vicinity. Virtual edge with 4-member node makes the largest computational resource with the smallest virtual edge recreation. Due to the lack of vehicle, virtual edge cannot be established successfully, and transmitting tasks to the cloud for execution will take longer delay. With the vehicle density increase, the computational capability of virtual edge will enhance. In figure in the right, available computational capability calculated by Formula 17 in the paper. At last, its conclusion. We proposed the concept of virtual edge based on mobile edge computing to solve the shortage of computing capability at the edge of network. We also proposed the edge node selection method where the relative velocity between vehicles is considered. We used the simulation to evaluate the proposed method by comparing with other baseline approaches. These simulation results show that proposed method can generate more stable and efficient edge node as compared with existing baseline. Okay, that's all. Listen, I want to share about virtual edge collaborative computation offloading in VANET. Thank you for all listening.
Hello everyone, I'm here to give a presentation. The title of my paper is Design and Engine-Aware Computation Task Offloading Structure in Power Wireless Heterogeneous Networks. My presentation contains the following 5 parts: introduction, system model, and problem formulation, proposed algorithm, simulation results, and discussion conclusion. First, it is the introduction part. Mobile edge computing proposed by ETSI can reduce the need for large amounts of computation from mobile devices, which enables such applications through providing computation results in close to mobile users and at the edge of the radio access network. Computation offloading is one of the critical issues in MEC system. Generally speaking, computation offloading is made up of 3 phases: the data uploading, the task execution, and the result return. With computation offloading technology, the results concentrated mobile user can save injure and enrich mobile users' experience by fully or partially offloading computation-intensive tasks to the nearby other mobile users or MEC server. In this paper, we study a MEC system in which consider computation results backup pool among the MEC servers and investigate computation offloading structure with the objective of maximizing the utility of mobile users and the revenue of MEC servers. First, we donate the system model and formulate the main problem as a standard game problem. Then, we prove the existence of the game Nash equilibrium. Furthermore, we propose a global optimal algorithm, namely computation offloading algorithm, to tackle this problem. Eventually, the convergence of the algorithm is studied by simulation. Next, I will introduce the system model and problem formulation. This paper considers a multi-access network with multi-mobile users and multi-small base stations as shown in Figure 1. In the MEC system, between mobile user and MEC servers are connected with cellular links, and each mobile user is capable of communicating with other mobile users nearby via opportunistic networks, which communicated using short-range communication protocols, for example, Wi-Fi, Bluetooth, and Ether. When the mobile user chooses to perform the computing task by using its own CPU, we call this case is the local computing. This is the total delay in this case, and this is the energy consumption. In this case, the mobile user decides to offload the computation task to the MEC servers. This is average arrival rate of the computation task. And this is the total delay of computation task. This is data transfer rates, and this is the total energy consumption for offloading to MEC server. In this case, the mobile user decides to offload the computing task to help user by DT link. This is the transmission rights, this is the total execution, and this is the total interconsumption. Due to the computation resource limitation of the MEC server, there may be competition among the mobile users when making offloading decisions. Since the mobile users' offloading decisions are driven by the pricing scheme, these mobile users are indirectly coupled by the computation resource price. Moreover, the computation resource provider are also indirectly coupled through the price during the offloading process. In this paper, we define the utility of mobile users and the running of MEC servers. Then model the computation offload problem as a Steinberg game. The revenue optimization problem of the MEC server can be expressed this. Third part, we will introduce the proposed algorithm. In order to solve the above computation offloading decision, we propose a distributed algorithm. In the algorithm, each of MEC servers begins by randomly choosing both the amount of computation resource purchased from a network operator and its computation resource ceiling price. Taking into consideration that each of MEC server is rational, the price set by MEC server is greater than or equal to the computation resource cost. Next, it is simulation results and discussion part. To prove the effectiveness of the algorithm we proposed, we compare its performance with the other two baseline algorithms as shown in Figure 2. The algorithm we proposed can be considered as the optimal algorithm in terms of both the time complexity and the utility of the mobile users. In Figure 3, the computation offloading system with the proportional price structure has the lowest benefits. Thus, compared with the other two offloading structures, the CORE we proposed can gain the highest utility, whether it is a small amount or a large number of mobile users. Figure 4 illustrates the impacts of BCS computation resource price on MEC services revenues as the number of mobile users increase. It can be seen that all incomes in this case decrease when the computation resource price rises. Due to the limitation of the MEC server's computation resource, more computation task is capable of being offloaded to the BCS as the number of mobile users increases. Figure 5 shows convergence of proposed algorithm in terms of mobile users' utility and is a perfect proof that the system can reach the Nash equilibrium, which can further explain that the algorithm we proposed can not only get close to the optimal result by the low time complexity, but also it is stable. Finally, I make a conclusion of this paper. In this paper, we design a multi-level computation offloading structure and consider the heterogeneous of computation task and computation results back up while making offloading decisions in multi-access networks. Firstly, the computation offloading model is introduced for each computation structure. Then the main problem is formulated as a Steinberger game problem. Then the simulation results show the efficiency and stability of the proposed algorithm. That's all. Thank you.
Hello everyone, I'm here to give an oral presentation. The title of my paper is Catch Enhanced Task Offloading for eIoT with Mobile Edge Computing. My presentation includes 5 parts: introduction, system model, problem formulation and the optimal solution, simulation results, and discussions. Conclusion. First, it is the introduction part. Mobile edge computing can meet the exponentially increasing computing requirements, and with its advantages of being more efficient, smarter, and more flexible, it can be well adapted to smart grid scenarios. However, most of existing research contents of the eIoT focus on the research of computing offloading and the content caching separately, ignoring the problem of reusability of some computing results. eIoT technology has developed rapidly in recent years, and a variety of inspection robot applications have emerged. This trend is expected to continue in the coming years. This paper considers the certain content caching capabilities of the MEC system itself and aims to design a cache-enhanced MEC eIoT. In this paper, we describe the MEC-assisted task calculation and offloading process in the eIoT. We use the storage capacity of the MEC server to catch the high hit rate calculation results can be reduce the resource consumption of repetitive operation. We propose the cache-enhanced computing offload strategy and collaborative scheduling algorithm in the eIoT. Next is the system model. Our transmission model considers not only the offload delay, but also the delay of return result. In the transmission model, a mode in which a base station and a MEC server are deployed in cooperation is used, and the combination is recorded as access point. The cache-enhanced offloading scheme is accessible to scenarios where multi-robot terminals carry multitasking. In the system model, we will model the proposed network, a cache-enhanced MEC system that provides services to inspection robot terminals as shown in Figure 1. Based on the existing 5G version specification, the inspection robot can communicate with AP. During the one-way road patrol, the distance between the robot and the AP can be obtained according to the following formula, where R is the horizontal distance between the road and the base station expected by the inspection robot. L is the coverage distance between the AP and the speed of the robot is V. Let B and det denote the channel bandwidth and the path loss exponent respectively. The transmission model takes both the uplink and the downlink, so the transmission power P and the channel feeding coefficient H should be considered in 2 cases. High-speed mobility is an important feature in eIoT, which causes on D changing faster. Therefore, the average transmission rate is used to measure the uplink and downlink data rate of the inspection robot terminal. Typically, a task can be modeled as a profile with 3 parameters. The 3 parameters represent the task input data size, computation intensity, and the maximum allowable delay respectively. The task input data size and the computation intensity are linear as similar to much existing research. The MEC server has a certain storage capacity as a computing device deployed to the edge of the network. Moreover, as part of the AP, the MEC server can be directly connected to a dedicated caching device. Based on its cache capability, the AP stores some task results. When the requester hits the content stored in the cache, the calculation result can be directly obtained. Let C denote the cache action. Here C is equal to 1 indicates the action of the task N hitting the cached content, and C is equal to 0 is opposite. The limited cache capacity is as follows. Next, I will show you the problem formulation and solution. The scheme calls for increased utilization of MEC. In addition, caching reusable results can increase the scalability of the system and reduce resource consumption, latency, and cost. Then, we propose a collaborative scheduling algorithm to guide the task requester to do joint computing offloading. Indeed, a requester may carry multiple different tasks, the set and number of robots who need to execute task N at the random system task state X, where I denotes the indicator function. Next, the requester starts the operation of offloading the task N. Under the influence, the operation delay and the backhaul delay can be presented as follows. In summary, the total latency of computing offloading can be expressed as follows. In this paper, how to get task popularity and catch high hit rate content is not our focus, since caching is a technology to enhance MEC computing offloading. This scheme ensures that the MEC server has sufficient computing power and reduces the delay for part of robot terminals. When considering the task requester set, the problem of optimizing the total latency can be formulated as problem 1. In problem 1, C1 indicates that the cached result cannot contain all task types, which is determined by the actual conditions. C2, if the cache-enhanced system still could not guarantee that the task is completed within the maximum tolerance delay, other calculation methods need to be considered, and C3 ensures that the situation does not occur. By solving the problem 1, we can optimize the total latency. Task offloading should take into account the impact of pricing strategies. Our collaborative scheduling algorithm can jointly consider the utility value and the delay tolerance parameter to improve the availability of the cache-enhanced offloading strategy. The utility value U is used to describe the relationship between resources and cost, can be given by as follows. We use the processing latency to describe the total utility value. Next, it is the simulation results and discussion. In this section, the effectiveness of our proposed scheme will be demonstrated by simulations. Figure 2 shows the relationship between the amount of buffer and the required resources. When the buffer reaches 40 million bits, the slope of the curve is significantly reduced. At this point, the MEC needs to provide processing 40 billion cycles per second power for unchanged computing tasks. Figure 3 shows the total latency of a cache-enhanced offloading and the popular MEC offloading scheme, similar to the results shown in Figure 2. When the cache reaches 40 billion cycles per second, the latency optimization result is quite obviously. Therefore, C is equal to 40 million bits is determined for subsequent research. In Figure 4, the strategies and algorithms proposed in this paper can save a lot of respective task calculation overhead for MEC servers, so the overall performance have always been better than other strategies. Figure 5 describes the total delay in the processing of the task when the number of robot terminals is increasing. However, the model proposed by us can save a lot of respective calculation overhead for MEC servers, so the overall performance has always been better than other strategies. Finally is the conclusion. This paper focuses on the application of popular MEC technology in smart grid. A cache-enhanced computing task offloading scheme is proposed, which uses cache-respective task calculation results to optimize system resources and processing latency. At the same time, a collaborative scheduling algorithm is designed to help smarter inspection robots to perform optimal calculation and offloading. That's all. Thank you.
Hello everyone, today I will present my work.
a secure crowdsourcing-based indoor navigation system. In this presentation, I will first introduce the background. Then I will present the system model and our proposal in detail, followed by the simulation results to validate our proposal. Finally, I give the conclusion and future work. With the rapid expansion of technologies such as Internet of Things, crowdsourcing-based indoor navigation systems have been regarded as a promising paradigm to tackle the numerous problems of indoor navigation. However, the effectiveness of crowdsourcing-based indoor navigation systems is based on the security of the system. Thus, it is an important issue to design an incentive scheme to ensure the security of the system. First, recipients consume the resources such as time and energy while completing the navigation tasks, which may cause the recipient to attack the crowdsourcing-based indoor navigation system, so the incentive scheme should be taken into account. Second, attackers' behavior in crowdsourcing-based indoor navigation system is uncertain. Thus, how to establish an attack model based on system background is an important issue. Third, the players, the attackers, and the fork service platform are selfish and rational, with the goal of maximizing their utility. As a result, consider the existence of the attack. Maximizing the utility function of players becomes a challenge. Motivated by these challenges, we propose a secure crowdsourcing-based indoor navigation system. Next, I detail the system model of our scheme, which consists of the network model, social relationship model, and trust model. As illustrated in Fig 1, our mobile crowdsourcing network consists of the following three entities: requesters, the fork service platform, and responders. The set of requesters noted by U. Requesters are a group of users who have the requirements for location information. Responders and the set of responders are described as V. Responders are a group of people, service provider. Fork service platform is a completely trusted platform in the crowdsourcing-based indoor navigation systems. The fork service platform is the bridge between the responders and the requesters. In addition, the fork service platform has sufficient ability to detect attackers. Then, I introduce the social relationship model. It's clear that the social relationship between the I's requester and the J's responder is the aggregation from multiple social relationships and defined as Fij. Here, II is the social relationship set, which is denoted by II. When some special relationships such as friends, colleagues, relatives, classmates exist, On equals 1, otherwise On equals 0. To determine the social distance between requester, UI, and responder, Vj, HL is defined as the bounds for social relationships. When Fij greater
than or equal to HL, it is intimate. When Fij less than HL, it is unfamiliar. For each location request service, the strength and weakness of responders directly affect their service level. Then I introduced the attack model. Attack model is an important fact for off-serve and diff-serve game design in mobile crowdsourcing networks. The attack model is divided into two cases based on several factors that affect the ability of collusion. The first case is collusion with strangers in social relations. Thus, the intensity of attack between an attacker and a collusion requester whose relationship with the attacker is intimate can be calculated by lambda 1. The second case is collusion with people who are socially intimate. Thus, the intensity of attack between an attacker and a collusion requester whose relationship with the attacker is unfamiliar can be calculated by lambda 2. Here, G is the frequency of attackers. Next, I introduce our proposal with the offensive and defensive game formulation. We first propose the reputation scheme for the secure crowdsourcing-based indoor navigation system. Responders are motivated to provide positive services by designing reputation scheme. The reputation scheme is divided into two situations. When responders provide the shortest and the fastest path to the requesters, the reputation value of the platform is updated by R. Here, epsilon is the increment of reputation, and R0 is the initial reputation value of platform. When responders provide negative services, the reputation value of the platform is updated by this equation. Here, lambda is the degree of collusion. The value of the platform is always on the rise as they always provide positive services, while for malicious responders, since they provide negative services such as deteriorate navigation paths to satisfy their own demands for profit, which will lead to a decrease in their reputation value. Next, we construct an offensive and defensive game to model the interactions between the platform and the responders to maximize the utility of the system. In this game, the set of players is Ace. SA is the attacker. SP is the focus survey platform. The attacker's strategy is the probability of launching attack, denoted as X. The strategy of the platform is the probability of selecting supervision, denoted as Y. The purpose of the attacker is to maximize its utility, while the purpose of the platform is to maximize its utility with considering the security of the system. Therefore, the utility function of participants can be divided into the following four cases. In case 1, that is, when the responders choose the collusion strategy, and the platform choose the supervision strategy. As such, for the responder, the utility of the responder can be described as UAXY. Here, delta is the responder's profit as a percentage of total profit. Lambda is the degree of collusion. Phi is the weight element. KD is the total number of tasks. Alpha K is the income paid by the requester after completing task K. Beta is the quality of the navigation path provided by the attackers. C1 is the unit cost when the responder chooses the collusion. P is the probability of attack fail. W is the attacker's loss when the attack fail, and S is the attack's gain when the attack success. Similarly, the utility of the platform can be described as follows. Here, D1 is the cost when the platform chooses the supervision strategy. J is the gain of the platform when the attack fails, and B is the loss of the platform when the attack succeeds. In case 2, that is when the responder chooses the collusion strategy, and the platform chooses the no supervision strategy. As such, for the responder, the utility of the responder is defined as this equation. Similarly, for the platform, the utility of the platform can be described as this equation. Here, D2 is the cost when the platform chooses the no supervision strategy. In case 3, that is when the responders choose the no collusion strategy and the platform chooses the supervision strategy. As such, for the responder, the utility of the responder can be described as this equation. For the platform, the utility of the platform can be described as this equation. In case 4, that is when the responder chooses the no collusion strategy and the platform chooses the no supervision strategy. As such, for responder, the utility of the responder can be described as this. And for the platform, the utility of the platform is defined as this equation. Then, based on the above analysis, we can obtain the equilibrium solution by using replicator dynamic equation. We first define the replicator dynamic equation of the system, which is shown as this equation. The gain equilibrium solution can be obtained by letting the replicate dynamic equation equal to 0. Next, we give the optimal solution. The optimal solutions of the platform and responders, which are shown as this equation. After introducing our proposal, we then give the performance evaluation. First, I introduce the simulation conditions. There are 10 mobile users and 1 platform in the mobile crowdsourcing networks. The increment of reputation is selected from the interval 0 to 1. The initial reputation value is set as 0.5, and the degree of collusion is selected from the interval 0 to 1. By comparing with the fixed scheme and the linear scheme, we evaluate the utility of the platform. Fig 2 is the utility of crowdsourcing platform on the different Fig 2 is the utility of the system on the different degree of collusion. It can be seen that the proposed scheme outperforms the conventional schemes. In the fixed scheme, without considering reputation match scheme, the probability of attack is fixed. Thus, the utility of system is basically unchanged. In the linear scheme, the probability of attack is proportional to the degree of collusion. Then, the utility of the platform decreases slowly with the degree of collusion increase. In the proposed scheme, the probability of attack is determined by the observe and diffuse game theory, so that the system can obtain the maximum utility. At last, I summarized our paper and give the future work. We proposed a secure CINAs that can provide the requester with secure and accurate indoor navigation services. We propose a reputation scheme that considers malicious responders with different attack capabilities and illegal profits. We construct the observe and diffuse game to model the interactions between participants and obtain the optimal solution. Numerical simulation results have been shown to prove that the proposed scheme outperforms the conventional schemes. For the future work, we will further consider multi-stage collusion to enhance the security of the system. Thanks.
Okay, thank you, everyone. And first, I would like to thank the program committee and the organizer of the conference to invite me to give a online talk. And my name is Liang Zhao, and I'm from Shenyang Aerospace University. And today, the topic of my talk is intelligence-empowered vehicular networking. And I will just give a 1.5 hour talk, and so I just divide my presentation to 4 parts. And first, I will give a brief introduction to myself, and I will show our progress of my team and my research group, and about the vehicular networking and the air-ground vehicular networking for the second and the third part of this talk. And we'll also talk about the future of the vehicular networking. And as introduced before, I'm from Shenyang Aerospace University, China, and my research interests include vehicular networks, space, air, ground, mobile edge computing, and I have authored about 90 scientific papers and several papers published in top journals and conferences. And I have applied the more than 40 patents and organized many conferences, including the IEEE IVCC and ScaleCon and other workshops. And I'm currently associate editor of the Frontier and served as the guest editor of the IEEE Transactions on Network Science and Engineering and some other journals. And before go further to talk about the vehicular networks, I would like to show you the future of network and the beyond 5G and 6G network. And here is the definition that defined the scenario of the IEEE future roadmap for the networking. And here are some revolutionary applications for the 5G and the 6G, including the mobile healthcare, we have the wearables and the IoT and the smart logics, telemedicine and VR, AR, and so forth. Many applications will be realized by the B5G and 6G. And for realizing the B5G and the 6G and these applications, and we need ubiquitous intelligent connectivities and computing for realizing these applications. And that's why we want to study further about the multi-hop vehicular networking and air-ground networking. For both multi-hop networking and air-ground networking, we aim to extend the coverage of the devices. We want to use the multiple hop technique to extend the coverage and to realize the 5G and the 6G. Here is our first reality of the vehicular ad hoc networks. So for my background, for my PhD research topic, it was about wireless mesh networks, which is comparably static networking for supporting the urban wireless broadband. And after leaving my first job, the job back in Hitachi Research and Development in Beijing, and I joined my current affiliation, Shenyang Aerospace University, and I chose the vehicular ad hoc networks because as my topic, because my previous research interest include the VANETs, multi-hop, and my research area in Hitachi was intelligent transportation system. So I combined these two strong parts and started the research in the Vehicular ad hoc network. And I want to show you the features of the Vehicular ad hoc network, which is so-called VANETs. And the size of the first is the size of the network. Second is the node mobility. And because it's the VANETs, and the major nodes are the mobile nodes, which are all the vehicular nodes. So you can see that all the nodes are mobile, and with high speed and moving within the streets, right? And the topology and the network density varies among different areas, because you can see in some urban area the density is very high, right? And in the suburb area in some countries the density is low for the VANETs. And the hardware, compared to other types of the ad hoc networks, such as the mobile ad hoc networks or the wireless ad hoc network, which is so-called WSN, and there's no energy constraint in vehicular nodes. So we have some new features for the VANETs, and back to the 2016, about 5 years ago, we started this new project, and we intended to apply some intelligent technique to study to generate the new routing protocols for the VANETs, and to improve the routing protocols like a GPSR, which is a traditional VANET routing protocol. So we used the SVM as a support vector machines to study the driving behaviors of all the drivers by study the behaviors. We will model one routing metric which will help our routing protocol to select the best possible next hop node in this scenario. And after this work, we started the study of the software-defined vehicular network. Why we want to introduce software-defined? Because for the traditional VANET, it is distributed vision, and all the nodes will organized independently, right? So we introduced the software-defined feature to this the VANET, which will bring new strengths to the VANET, and will put some centralized computing power to the VANET, where the SDVN, which is short for software-defined vehicular network, decouples the data plane and the control plane, so it can separate the data forwarding function and the network functions. So here is the scenario for the SDVN we introduced. But there is still some open issues for the SDVN, right? Because the traditional SDN, because we combine the SDN and the VANET together to have the SDVN, the traditional SDN does not have some constraints like the vehicular network, such as the high mobility and so forth. So we need to study the following points, such as the lack of research in the dedicated trajectory prediction algorithm, because the vehicles move very fast on the street, and because we want to use the controller of the SDVN to obtain all the information of the leaf nodes of its vehicular information from the vehicle. So it will generate a lot of overhead. So how to reduce the overhead, and how to conduct efficient routing algorithms, and how to apply more AI technique to the routing management in the controller and so forth. So these are all the open issues. And here's some future directions for the SDVN as well. So we can study such as the RCU selection, cluster routing, and the prediction learning-based routing metric, time-dependent routing, and so forth. And actually, we followed the path of we studied in the last slide, and started some new research for the SDVN. First work after that is the hybrid SDVN work. So for the hybrid SDVN is we have the centralized the controller to generate the routing policies for all the VANET nodes, VANET vehicles. And the VANET vehicles will organize just like in VANET. And the centralized the controller will just distribute the routing policy, and it will study the behaviors of the nodes, and generate and switch the routing policy between among all the routing policies in its policy pool, and then distribute the policy. And once the vehicles get the policy, it will switch from one to the other, and like from the AODV to GPSR. And this is the hybrid SDVN. And in this work, we studied how to extract the road network information, and we also use the OSERM, the online learning online learning machine to model the real-time training. And we also have one other work published in ICC 2019, which is concentrated on the fully centralized SDVN. Because, as we mentioned before, and our work was one part of the open issue is how to apply the prediction to predict or foresee the trajectory of the vehicles. So we need to know that, because we all in the controller, once we compute the routing path, or so-called flow table, the flow table is computed for the future time. So we use HMM-based network to predict the trajectory of the vehicles, and will help us to generate more accurate routing paths in the controller. And for more for more intelligent techniques we involved for the vehicle network, we also use the fuzzy logic, right, for generate the routing paths, and among the different paths, or inside one path. So we divide the path, one routing path, or divide the road to interpath and the intrapath. And for interpath and the intrapath, we use different fuzzy sets to compute the best routing path, and to obtain the routing path, the most efficient routing path. And this work is published in the attribute transactions on fuzzy systems. And we want to predict, do more concise prediction. So we used the more intelligent technique, one learning network called generative adversary network GAN, to train and learn the driver's behavior from the historical trajectory data. And our discriminant network consists of two independent networks, which are applied to receive the input and output data here, and of the generated network respectively to achieve better prediction precision. So this work is published in the IEEE IoT journal. And okay, this is all about our work about the vehicle networks. And the other part of the presentation is about how to use the air-ground networking, because we see that in some part of even in the urban area, some part the nodes and the vehicles are very sparse. So we need to use some actual node or actual device to reach the sparse node. So the one thing brought to us is the UAVs, right? So we want to use the UAV to assist the networking and the computation for the vehicle nodes. So once we talk about the UAVs, we need to do the path planning, right? The path planning for the single UAVs and the multiple UAVs, right? We have some work for the path planning for the single UAVs, and also we also need to do the clustering. When we have multiple UAVs together, and how to use these UAVs to avert the collision and to improve the secure communication in the scenario of the multiple UAV cooperative control flight, and then use these multiple UAVs to cover one area which is sparse of the vehicles, right? So in this work, and we use the flocking algorithm to enable the multiple UAVs to fly cooperatively and reach a relatively stable position, and so we achieve very good results. And this work published in the Computer Networks. And further, we studied the UAV-assisted VANET, and we proposed a novel collaborative network architecture integrated the drones, the UAVs with the VANET, right? So we want to know where we also called for which position we deploy the UAVs the best, right? So we need to deploy multiple UAVs in the urban area, one certain area. So we want to know how to evaluate the criteria, to detect the criteria to evaluate the demand of the drones, and we want to consider the multiple objective of the VANET and build an evaluation function for the optimization. And so we want to have the results and to find the optimal distribution for the multiple UAVs to assist this urban VANET. And we model this as a multi-module optimization problem. And in order to reduce the energy consumption of data transmission, the optimal stopping based on target UAV selection mechanism is also proposed, right? And as we said, we model this as a multimodal optimization problem, and we want to solve it and then we design one specific multimodal optimization algorithm, and namely the multimodal nomad algorithm, inspired by the migratory behavior of the nomadic tribes on the Mongolia prairie. And it's called MNA, right? It enables the instant dispatching of the multiple UAVs to the best service positions in order to enhance the efficiency of the UAV or drone assisted the VANETs. So we built this like swarm intelligent algorithm to search for the best dispatching positions, right? And also for the networking, and we have one recent work published in on IEEE transactions on industrial informatics. And we have this kind of industrial scenario. We want to use the UAV to assist the software-defined deterministic networking for the ground and both the ground vehicles and other nodes on the ground. And this scenario of novel features requiring the deterministic networking transmission provided the UAV. So we analyze it, and these areas demanding some transmission and the outbound network infrastructures are both sparse. So we proposed one new topology, and a coordinate-based global topology view is built to enable the forwarding resource management and control and multiple generating. So we built the view by embedding the backbone UAVs into the initial location-based view. And we also proposed one hop limited time synchronization approach to improve the synchronization accuracy to guarantee the deterministic networking. And here we also have one geometric multipath generating method, right? Which work on based on the topology view I mentioned before, and which is to propose to enforce the transmission reliability and reserve the resource for the deterministic networking. And here we have another work, which is not obviously it's not only for the networking, because for the UAV and for the UAV to support the vehicles, we also need the UAV to support besides the networking, we also use the UAV to support the vehicles for computing. So once we talk about computing, the most recent research we have is the mobile edge computing based on the UAVs. We have several works on that. And the first one is the UAV assisted vehicular computing for the catching. So we need to have two parts: one to catch the information for the UAVs and to reduce the latency required by latency generated by the transmission from the vehicle between the vehicle and the backbone servers. And the other part is for the offloading. Once we have a work generated by the vehicle, so how the vehicle will decide to transmit the task, and how the task will be handled by either the UAV or the vehicle itself or the far end server. So we started the two parts of the MEC, which is mobile edge computing. And the first one is catching, right? So we proposed the three-layered vehicular catching architecture, right? And we involved the airship here and the UAVs and the vehicles, and which this architecture provide real-time UAV scheduling for the content request and guarantee the accurate catching assignment. So DQN, which is one deep Q learning network we used, and use this DQN to learn the best information we need to catch by the UAV, and we didn't distribute the UAV with the catch the information to support the ground vehicles. Then once the vehicle has some information requested, it might have some information already catched by the UAVs. Then it will request the UAV to send the information to them. So it will reduce the latency if we compare with it requesting all the information from the far end servers. And For the offloading, we propose one SDN-enabled UAV-assisted vehicular computing or delay architecture. And here is our architecture, right? We have also 3 layers: data plane, and the sky layer, and the ground layer. Also, we have a control plane. So we'll be deploying a UAV to cruise along fixed trajectories in the region of dense buildings and sparse infrastructure, and the vehicle's users can offload computation tasks to the UAVs, and the UAVs can serve as a relay node to transfer the offloaded task to the vehicle users to the MEC servers. So we formulate the problem as a multi-vehicle user offloading game and design the decision-making algorithm and for our scenario. So we publish this work in the IEEE transaction on TITS. And last, we want to talk about the future of the network, or more detailedly, the future of our vehicular networking. And for the future, and in my idea, we need to have a digital twin, which also we can say is intelligent digital twin for our vehicular networks. Because vehicular networking is very complex, and we need to always compute and always generate new routing paths and learning new information from the routing info statistics or vehicular informations. And we can have one digital twin for that, intelligent twin for that. So we proposed the new architecture called IDT SDVN. It's also called Intelligent Digital Twin SDVN. So it has 2 parts: physical network, which is the real network, and the IDT SDVN parts, which is a virtual digital twin of the real network. And for the controller in here, the controllers are set up to calculate the routing request as well as the scheduling the vehicles when acting as a MEC server. On the other hand, the IDT part as the virtual network is conducted by the controller to model and verify the instant learned functional models. So the virtual part will learn or will gather all the information from the physical network, and it will learn and then generate the new models, including the new routing models and the decision models for the physical network. And then it will evaluate all the generated models in multiple instances of the virtual networks here. And then after evaluating, it will select the best model and then apply the best model to the physical network, right? Then the physical network will use the applied model and work in the network as a networking routing protocol, for instance. Then once it generates more information or more errors, right, it will feed all the information to the virtual one, and the virtual one will then train again. So it's like the virtual network and the physical network, the IDT and the real network will work together to generate instantly and to work together to generate the best routing models, right? Right, then we will have more things to do to achieve that. We need to study how to apply more learning algorithms and the dedicated learning algorithm for the networking, and we'll consider the special demands of the intelligent algorithm for the networking. And also we need to study how to switch from the virtual to the practical, and which is the best time to do that. As well as we need to study the adjusting fund feeder or the intelligent strategies. Okay, so I think this is my talk, and it's half hour. Thank you for listening. And if you have any question, you can ask me directly or send me an email. Right, send me an email. My email address is ljao@saud.edu.cn. Thank you very much.